So do you think maybe I should start sharing now?
I would ask you not to do that yet.
Yeah.
Okay, so it's time to start. So welcome to the third parallel session of the BSM track. I'm Michal Malinsky. I'm your first block chair. So today's session is not yet very attended, but I believe people will start joining like very soon. We will have a couple of interesting blocks today. The first one is going to be on lepton works. Then we turn into baryon and lepton number violating searches, some lepton flavor violation, and then we will peep into the dark world. I would just like to remind you about a few technical details. I will use this kind of fancy device to remind you about the approaching time limit of your slot. Please ask your question or save your questions for after the talks. Use the raise hand feature of Zoom, or if it's urgent, feel absolutely free to post your question to the Mattermost channel, which is constantly checked by the two of us, me and my co-chair of today, Yu Nakahama. Okay, I think we can start. So the first speaker is Bel Kilminster, who will start the lepton quark session. Ben, please.
Let's see. Am I sharing now?
Yes, please go full screen.
Okay, so we're good?
Good.
Okay, great. Let me just make this easier for me to see. Okay, so, and one thing is I can annotate here, I can make a little pointer for myself. Okay, so I'll be talking today about leptoquarks, my little relation here to flavor. And here we go. So first, one of the first things we notice when we look at the standard model is we see a similarity between quarks and leptons, this sort of SU2 grouping that we see. And we often wonder, is there some underlying symmetry that would explain this? Another puzzle that we have, which is theoretical, is why are there 3 generations of identical partners? So we've got the first generation, second, and third, and only the Higgs boson can actually tell the difference between these. It gives them different masses. And while we know about this, this Yukawa coupling, it's essentially arbitrary. So we don't know why the Higgs boson can tell the difference. How does it tell the difference? And as much as we do precision measurements of Higgs couplings, we're not going to actually figure out the why or the how. We need some new physics to actually tell the difference between, for instance, an electron, a muon, and a tau. So I'm going to try to relate this to this talk today. There's some other experimental puzzles we have. The magnetic moment of the muon has had a long-standing discrepancy. In fact, the first The first G-2 measurements were done at CERN by Leon Lederman, 50 years ago, something like that. These days, now we have a 3.7 sigma discrepancy, and this has been fueled by a lot of theoretical progress, which has now given us a very small uncertainty compared to the experimental uncertainty. So now we wait for the new results from Fermilab. Other experimental puzzles, which you'll hear about more in this session, is this RK star ratio of B to K mu mu over K to EE. There's a deficit here, you can see, with respect to the standard model. The angular distribution, the angular analysis of this, looking at the EFT and the Wilson coefficients, there's a 3.3 sigma discrepancy. Ratios of B to D decays with D to tau nu over mu nu has a 3 sigma discrepancy, and there's some other discrepancies as well. So we see a lot of these kind of what we call flavor anomalies. So could there be a BSM explanation for this? There's a lot of explanations with new heavy mediators that maybe have some lepton flavor universality violation that could maybe tell the difference between the generations, and new left-handed currents which seem to be preferred by the data. So one way we can do this is with leptoquarks. A leptoquark could be scalar or vector. It's a boson here, which has a coupling to leptons and quarks. So this is a particle that carries lepton number, baryon number, and color. It's, of course, mediated by this coupling, which I label lambda LQ through the talk. And a second here. And, of course, it has fractional charge. And we see, for instance, that it can be 1/3, 2/3, 4/3, or 5/3 because it's carrying this, it needs to decay to quarks. So if we want to now try to explain these anomalies, when we look at this RK star anomalies where the decays to muons divided by the decays to electrons is less than 1, so we need something to make this smaller. Whereas the decays to tau nu over mu nu are actually greater than the standard model value. And so we see these Feynman diagrams for standard model processes for some of these. And so now if we add in leptoquarks, we can create the same final state, but by giving it this extra component. So one explanation for these, which I kind of mark here, is a combined explanation for these ratios, but also the angular anomalies. It puts a flavor structure into leptoquarks. So for instance, we look at this matrix here, which relates for instance, the 3rd generation particles. So there's the relation of B tau and top to neutrino. And we see this matrix is mostly 1 in the 3rd generation. So this is basically saying that leptoquarks are essentially 3rd generation leptoquarks in their flavor structure. Another thing to note is this negative term here, which basically tells us we have destructive interference, which is what we need to get this RK star ratio less than 1. Leptoquarks, I won't say much about this, but they could help also explain this G-2 anomaly in this sort of penguin-like diagram here. So can we search for leptoquarks directly? In fact, that's this talk. So leptoquark production at the LHC can be pair production of leptoquarks, single production, or a non-resonant T-channel here. And these are some couplings just to show you that the pair production is mediated by the strong coupling, whereas these other modes here depend on lambda. And so they're kind of looking at the pros and cons of these different channels. We have a pretty large QCD production for pair production, and this produces resonances, and it's largely independent of this, where it's independent of this lambda coupling, except in the decay here where we would have some lambdas. The single production depends on lambda squared. we're going to get a PDF suppression because this quark is typically a B quark or a heavy quark. And so we get a PDF suppression for this. And we also get a wide resonance, which I'll spend a bit more time on later. And then the non-resonant has a lambda to the fourth, but there's no resonance here. And we also have to produce multiple Bs in order to produce this. So leptoquark searches at CMS, we have a range of these, and I'll be talking about a bunch of these ones. I want to point out the ones in green are results with 137 inverse femtobarns, our full run 2 data set. And we have a new result, the first time shown today, which I'll spend some time on. Okay, so in the first generation, we can have leptoquarks that decay into an electron plus a quark or a neutrino plus a quark. And these searches are done with high PT electrons or electron and met and jets. We don't have any flavor requirements because these are, again, first generation quarks. And then what we do is construct leptoquark candidates which minimize the mass difference between the two possible combinations because this is pair production. So we can look at one of these distributions. This is a distribution of mass of the leptoquark. And we see kind of up to this 1.5 TeV range. There's a few different models for candidate leptoquark masses, and we have a background that's mostly Z plus jets. We can take one of these distributions, take a few other distributions here. This is dilepton mass, and this is ST, which is the sum of the PTs of the primary objects in the event. We can now use these distributions to optimize cuts as a function of leptoquark mass, and then use this distribution to make a counting experiment. So for each leptoquark mass, we make a cut and just count the number of events above that cut and put them on this plot here. And this gives us a good sensitivity to leptoquarks. When we look at this, we can now look at the leptoquark mass limits as a function of the cross section. And this is times beta, this branching fraction of the leptoquarks. And the way this is defined is beta equals 1 just means that the leptoquarks are decaying to charged leptons and quarks, whereas beta 0 is a neutrino plus a quark. And then we can have this sort of mixed state where we have one leptoquark. This is sort of a more democratic approach. We expect the leptoquarks to decay equally to both. And so when we plot these two as a function of beta, you can see that we do best. Maybe I have this, so I have to check here. Okay, so anyway, we basically have limits that depending on if it's 2 electrons plus jets or lepton neutrino plus jets, we have sensitivity in different regions. So in the second generation, we can do the same strategy. So I won't go into kind of building this up, but it's basically the same idea. We use these kinematic distributions to do counting experiments, and we can look in mu nu or mu mu plus jets and produce these limits. Again, we see them kind of combining to produce a better result, somewhere around 1.2, 1.3 TeV. Now moving on to third generation leptoquarks. Here, it turns out that some of our best results come from recasted top and bottom squark searches. And these are results with full 137 inverse femtobarns. So here we're only considering 1/4 of the cases where we get quark plus a neutrino. And just to show you, I have these diagrams for SUSY production, but you can see that how this would look also like leptoquark plus, so a sputum goes to a B plus neutralino, it gives us the same signature that we expect. The way these analyses work is they use this variable called MT2, where you look at the missing ET vector and basically loop over the trial vectors for 2 possible leptoquark neutrino components. and loop over them to produce basically the largest MT, so transverse mass of the leptoquark candidates in this case. So here, the analysis actually considers a large number of jet multiplicities and BTAG multiplicities for different HT ranges. So we basically look at this MT2 distribution in these three different categories here. And this gives us a large possibility to constrain the backgrounds. Also, leptons are vetoed in here. This is a hadronic final state. And these results, when we look at versus vector and scalar couplings for different couplings, so this is K equals 1 is sort of the Yang-Mills, K equals 0 is the minimal coupling. And as a function of these, we can set limits somewhere around 1.5 to 2 TeV. So this actually provides us our strongest constraints on scalar and leptoquarks through pair production, which I list here. So moving on to single leptoquark production, which we have here, where it's just mediated by this lambda. Just to say a little bit, we select these B's through the secondary vertex. Taus, we have a dedicated tau reconstruction for different types of taus. And then when we look at the tau decays, we can have taus decaying leptonically or hadronically. When we have two taus, we have kind of these tau had, or tau had with electrons or muons. And this gives us a range of different tau channels to search for, since we have these two taus. So going quickly through here, for each of these, we can look at a distribution of this ST variable, which in this case is related to the tau momentums plus the jet momentum and missing ET. We see pretty good agreement here with these different cases. And we move on to set limits. In this case, what we see here is the leptoquark mass versus the coupling. And the pair production gives us this limit, which is independent of coupling, whereas the single leptoquark production starts improving because it depends on lambda squared. This blue region is kind of the region where the B anomalies prefer the coupling and leptoquark mass to be. So the last analysis I want to tell you about is this democratic decays to leptoquarks. So leptoquark can decay 50% to tau nu or tau B. In pairs, that would give us a final state like this. A scalar leptoquark, which comes from a different theory to try motivated by the same anomalies, would decay slightly differently, top tau and B nu. But it turns out this gives us the same final state here. And also likewise for single leptoquarks, we can get a final state of top nu tau, and we get the same final state for scalar leptoquarks. So even though it's a slightly different decay. So our final states look like top nu and tau plus with or without a B. And this analysis basically considers the all hadronic final state, where we have top quarks which may be fully merged, partially merged, or fully resolved to give us the best efficiency over the high mass range. So looking at this results here, we can see the ST variable, again, for resolved states and for the boosted states. And we can move on. I won't say much about this. I wanted to just point out here, if you look at this slide, that I can say more about this later, that that the efficiency actually decreases as a function of mass for high lambda values. So I could explain that later if you're interested. But let me finish up here. So our results, when we go to look at this, we can look at the pair production and single leptoquark production. And we can move over here and we see our limits are around 1 TeV for scalar. And for vector, different couplings, our limits improve. We get up to 1.6, 1.8 TeV for these. So as a summary, it's hard to see maybe the text here, but you can see that we have limits on first generation leptoquarks, second generation leptoquarks that are somewhere around 1.5 TeV. And our third generation leptoquark searches can get upwards of close to 2 TeV depending on the couplings. So in summary, leptoquarks are motivated theoretically and experimentally. We have searched for all 3 generations at CMS, and we have some new results with the full data set. For our third generation searches, we have some dedicated searches for leading models that explain the flavor anomalies. So scalar and vector leptoquarks in different leptoquark decays, also considering both pair production and single production. And we're probing leptoquark masses up to 2 TeV, close, something like that. So we have more results in the pipeline. So you'll hear more about this in the coming months. Stay tuned. Thank you.
Okay, thank you very much, Ben, for the nice talk. I think we've got time for one or maybe 2 very short questions. Please raise your hands.
If there's no question, I could go back and explain that slide I skipped through quickly.
I do have a question. Like, I think around page 6, you mentioned that actually the data prefer left-handed currents. So what's exactly the piece of data that tells you this?
Yeah, let me see if I can. You're going to hear more about this in the theory talk later, but let me try to say what I can say on this here. So when they do the analysis of for instance, the LHCb data of this beta k star mu mu angular analysis here. So this P5 prime, the Wilson coefficients that you consider. So you have this sort of effective standard model Lagrangian, and then you introduce components like what would happen if there was some additional left-handed coupling or right-handed coupling or scalar coupling, and then you make comparisons of the actual data to the modifications you would get from this. And it turns out that left-handed couplings are preferred to fit basically these angular deviations that we see here. So there are models out there that attempt to also do this with other couplings. But I think it's hard to explain every ratio as well as the angular distributions unless you have a vector left-handed coupling to try to explain this.
Okay, thank you very much. So our next speaker.
Yeah, let me unshare.
Sure. Our next speaker is Yasuki Okumura from University of Tokyo, actually giving us the same perspective from the atlas.
Okay, so can you hear me well?
Perfect.
And can you see the slide as well?
Good.
Okay, yeah, so today I'd like to talk about the search for leptoquarks using the atlas detector following the CMS talk now. Yeah, the leptoquark is a hypothetical new particle which can couple to a lepton and quark at the same interaction vertex with respect to conservation laws, and it is predicted in terms of the grand unification theory, and it has a particular interest owing to the recent LFU test in the B sector, namely RD, RD star, and RK, RK stars. And as it is shown in the diagram here, the leptoquark can possibly contribute to the LFU anomalies with the tree-level interactions as shown in this diagram. And the characteristic of the scalar leptocoques can be described as following. We have the 9 Yukawa couplings for the 3 generations of quarks and leptons. And we have relative coupling to the charged and neutral leptons, which is often called as a beta parameter to control the branching fraction of the LQ to QL and Q nu. And in the Atlas physics program, we have the systematic yet simplified analysis strategies, and we have the several analysis running, and each of them are focusing on the final certain final state, which is a signature-based search. And each of them test target Yukawa coupling as a benchmark with various beta scenarios. And this time newly, we started to search the cross-generation coupling leptocoque models in our search strategy. And today I'd like to show the following 4 results of the leptocoque search, especially in the pair production mode for the scalar leptocoques. And they are the E mu plus jet channel, tau plus top channel, E mu plus top in the boosted regime channel, and neutrino plus top channel. And this is a leptocoque coupling matrix. And by having these final state searched, we can cover this large parameter space of the leptocoque of interest. Okay, then let's start the individual discussion for the analysis. First, about the E mu plus jet analysis. The target final state is LQ produced and decaying into the EEJJ or mu mu JJ. And here J stands for the light or charm or bottom flavored jet. And in the event selection, we selected the 2 energetic charged leptons and 2 energetic jets. And also we can require the small missingity to suppress the background from TT bar. And in order to have the best sensitivity for the B-lep and charm-lep leptocoque types, we have the further categorization with respect to the C tagging and B tagging result. And here we can reconstruct the leptocoque systems by having the LJ pair. The balance of the 2 invariant mass of the LJ system is a important parameter for this analysis. And the asymmetry parameter can be used to solve the combinations between the lepton and jet pairs from LJJ final state. And furthermore, this can be used to define the signal region and sideband regions to control the background without the signal contaminations for the unknown leptocoque mass. Okay, then the average mass of the 2 invariant mass is used as a final discriminant to test the signals. And with this final state, we can test 6 types of the leptocoque hypothesis, which is combinations of electron or muon and 3 types of jet flavors. And here, particularly, I showed the result for the mu B final state with 2 B tag categories. And this is the average mass distribution. And unfortunately, we didn't see the discrepancy between the data and the expectations as shown here. And then this information is interpreted first into the cross-section times branching fraction upper limit with 95% confidence level. And so we can compare the upper limit with theory expectations. And this time, this is for the 100% branching fraction case. And by testing all the various branching fraction hypotheses, we may have this exclusion limit in terms of branching fraction and leptocoque. And we have the best sensitivity for the 100% scenarios for this final state search. And this is all the result. And we tested all the 6 types of signals. And unfortunately, we didn't see the significant excess for all the channels. And then the exclusion limit is set in terms of branching fraction and mass for all the possible 6 channels, as you may see here. And here we have the best knowledge for the leptocoque hypothesis. And for the 100% branching fraction case, 1.7 to 1.8 TB leptocoque, scalar leptocoque is excluded for all the possible combination between the light flavor and the jet flavors. And even for the smaller branching fractions, we have the certain such sensitivity up to 800 GB. for all the possibility of the combinations. And then second search is a leptocoque decaying into tau per stop. And this is the first time in the atlas to have the dedicated search for this final state. And this is the target final state is T tau T tau. And due to the various decay topology of the top and tau, we cover various final state in the analysis to maximize the acceptance of the analysis with respect to the multiplicity of the light leptons and also the multiplicity of hadronically decaying tau leptons. And further, we have the categorizations of the event into the signal region, validation region, and control regions. And typically, we will use kinematic observables, which can separate the signal and the background. And effective mass is one of the important parameters for that. And it is optimized for the high mass leptocoque signals. And this time we started to use the brand new recursive neural network tau ID for the hadronic tau with excellent efficiency and rejection factor. And finally, we performed the simultaneous fit of the 22 signal and control regions with M effective as a final discriminant in the signal region. And the background is estimated in the following way. So for the TT-bar background, we need to have the improvement in the high M effective end, which is understood in the analysis of the control regions. And we apply the so-called kinematic reweighting factor, which is derived in the analysis of the TT-bar control region. And we have the quite nice improvement for the TT-bar model, and we have the good estimations for this background. For the fake tau background, it is estimated with the Monte Carlo, and we have the correction factors derived in the fake tau control regions. And for other important background, the normalization is determined by a fit in the control region. And this is a summary of the all control regions after the fit, and we have the good control. And with this knowledge, we can expect the spectrum of M effective in the signal region. And this is one of the signal regions. And this is a summary for all the signal regions, all the 7 signal regions. And unfortunately, we didn't see any significant excess in the analysis. And we calculated also the local p-value for the various mass hypotheses. And we have the agreement with respect to the background only models for all the mass hypotheses. But it is remarkable that if we had the signal, indeed there is a big chance to even observe the signals thanks to the LHC energy and also the precise background estimations, as you may see in these dashed lines. And then this information is used for the exclusion limit as a function of mass and branching fraction. And for the 100% branching fraction case, we excluded up to 1.4 TB leptocoque hypothesis. And this is quite a big improvement from the previous result of 920 GB from the 36 investment bar. And this is the most stringent limit for that. And furthermore, for the branching fraction 0.5 case, still we have the most stringent limit for the scalar leptocoque, and up to 1.2 TB is excluded from our analysis. And then the third one is the leptocoque decaying into the E plus boosted top. And the target is the high mass leptocoque, and therefore we have the boosted top, and we have the isolated electrons. And the selection is we require the 2 leptons and 2 large RZ, and 0.4 small RZ is included in the large RZ. And this time, we deploy the machine learning technique for the multi-class classifier to separate the leptocoque signals, TT-bar background, and G plus jet background. And kinematic observables in the rest frames of the intermediate particle in the decay topology given by the recursive jigsaw technique are used. And also the jet substructure variables are used to have the best separations only in the muon channel. And this time we use the parameterized classifier to be used at all the leptocoque mass point with the optimal sensitivity without individual BDT trainings. Okay, then this is the result, the final fit result. We have the two control region for TT bar plus jet, and the signal region is using the 3-beam spectrum of the BDT score. And we saw the slight excess for the various mass hypothesis, and this is a result for 1.5 TeV for both electron and muon channel independently. And the maximum p-value is found to be 11% for the electron channel at 1.5 TeV hypothesis. And in the muon channel, independently, we found a slight excess corresponding to 10% p-value at 1.6 TeV. And taking this into account as a null result, if we took the exclusion limit, it is up to 1.5 TeV leptoquark mass for the 100% branching fraction case. And the expectation is actually more than that, like 150.60 for both channels. But due to the slight excess, we have this weaker limit for that. But this is still the most stringent limit for this type of the quarks. And also, I would like to remark that this is the first time to have the ETOP cross-generation channel search explicitly done in the atlas. Okay, then finally, the leptoquark decaying into the neutrino plus top channels. So as shown in the CMS talk, so thanks to the similarity of the event topology between the scalar top pair production and the leptoquark pair production, we can reuse the scalar top pair production search result to test the leptoquark signals. And we use the TT bar plus MET search in the final state, in the full hadronic final state. And this is a search strategy for the scalar top as a function of a scalar top mass and the neutrino mass. And if we have the zero mass neutrino, this is exactly the same for the leptoquark signature. And the so-called SRA and SRB is optimized for these event topology. And we used them as signal regions for our leptoquark test, which require 4-jet and 2B jet. And also the larger jet is reconstructed due to the boosted regime. And 1.2 jet is used for top candidate and 0.8 jet is used for the double candidate. And this is the yield summary for the signal regions, particularly for signal region A and B. We don't see any excess. And this information is used for the upper limit of the cross section and also the exclusion limit in terms of branching fraction and leptoquark. And for the branching fraction of 100% to T new case, we have the best sensitivity and we excluded up to 1.2 TeV as you may see here. And this number is compatible with a scalar top pair production search for the light neutrino assumptions. And this is due to the similarity of the production process between the leptoquark and the scalar neutrino. And yeah, also I would like to mention that for this lower branching fraction case, the neutrino dominant branching fraction scenarios, this has pushed the limit a lot by having the full data of the LAN2 from the SUSI analysis. Okay, then finally summary. The leptoquark signals are being looked for with the data taken by the atlas in a strategic way, covering various final state and types of the leptoquarks. And we are exploring also the new cross-generation leptoquark models such as B mu and TE. And we have quite a lot of the new result in this presentation. And we are using the cutting edge technologies to increase the sensitivity in the atlas search, such as boosted object, brand new tau ID with a neural network, and charm tagging, and so also the machine learning technique. And no observation is found so far, yet the exclusion limit is pushed toward high mass due to the, a lot of effort, and also new models have been tested in the Atlas physics program, and more analysis is in progress, and please stay tuned. Okay, that's it.
Okay, thank you very much for a nice talk. So it's time for questions. Please raise your hands. Okay, I may have a question. Actually, you were talking about top jets, and yesterday we were hearing about some novel top tagging algorithms used in Atlas searches for resonances in the TT bar production. So, are you sharing this know-how from that group? Do you use this?
Yeah. So it depends on the search, but for instance, for this analysis, we are using the jet substructure variables in the as an input for the multi-class classifier. So in that sense, we are sharing the effort in the Atlas wide.
Okay, thank you. Other questions? Okay, if not, we should thank Yasuyuki and perhaps move on to Jonathan Kriwald.
Okay, thanks a lot.
Good morning. Let me share my slides. All right. I want to thank the organizers for giving me the opportunity to speak here. And I will talk today about standard model extensions to explain the B anomalies, which feature a single vector leptoquark. And this is mainly based on some work we did last year with Chandan Hati, Jean Olof, and Anna Texera. The main motivation is, of course, to explain those very exciting hints towards lepton flavor universality violation we see in data. And lepton flavor universality is an accidental symmetry of the standard model. So those deviations we see in RD star and RK star are an exciting hint of new physics. And in recent years, this naturally caught a lot of attention in the pheno community. And many models have been proposed, for instance, with heavy Z primes or even light Z primes, scalar leptoquarks, composite Higgs models, R parity violating supersymmetry scenarios. And one particularly appealing physics scenario is a TV scale SU2 singlet vector leptoquark, which is called V1 or U1. And it couples down-type quarks to charged leptons and up-type quarks to neutrinos. And up to CKM and PMNS elements, the couplings per generation are the same. So the down-type to charged lepton couplings and the up-type quark to neutrino couplings are the same. The only difference are CKM and PMNS elements. And as it has been pointed out by Andreas Krivelin and colleagues like 2 years ago, in those type of constructions, RG running effects are important because we're explaining both anomalies in a single type of model. And if we take a closer look to this plot here, you can see here likelihood fits on both anomalous channels, like in the neutral current and in the charge current. Also on the B2S mu observables, which includes the branching fractions and the angular observables. And here on the x-axis, you can see the B mu and S mu coupling, which of course mainly drives the neutral current. And here you can see the B tau and charm tau neutrino, which is the same up to CKM as B tau and S tau, which mainly drives the charge current. But if you look at this yellow ellipse here, you see that in the angular anomalies, or in general for the B2S mu data, there's a strong correlation between the tau and the mu couplings. And this is because of a G-running, which will mix the C9 tau into the C9 mu. And if we look at the recent LHCb data, like from March in the B2K mu, this effect gets even stronger. Here you can see this V minus A kind of new physics hypothesis together with a second contribution, which is universal for tau, mu, and for mu and electron, not for tau, but it comes from tau. So if we generate a large tau operator to explain RD star, and run it down to the observable scale, and then this will generate a universal contribution. And the dashed lines here describe the data before this year. And you can see that it was compatible with 0 at 1 point log sigma. And now with the inclusion of the new data, it's at 2 point a lot. So this even strengthens the case to have a combined explanation between the charge and neutral currents. And it also strengthens the case for this particular leptoquark. So let's look at specific model realizations. If we want to build a gauge model of the leptoquark, rather than having it as a composite particle, then we have a problem because gauge couplings are strictly universal. So how can we achieve lepton flavor universality violation? So first step approach is to use the unitary quark-lepton misalignment to generate somehow a flavor structure in the leptoquark couplings. But as it turns out, this is completely ruled out by lepton flavor violation. Yeah, we need to do something about it. And then a possibility is to extend the fermion sector of the standard model. We could think about vector-like quarks. We thought about vector-like leptons, which will then mix with the left-handed standard model leptons. And if you add those, you will extend the leptonic mixing matrix. So here you have, in this block matrix is V0. This is like the unitary mixing between the standard model leptons. And this beast in front encodes the mixing of the heavy states with the standard model leptons and also Monson states. This is inspired from neutrino physics, where you use this to explain not to explain, but to calculate the mixing of standard model neutrinos with additional heavy states. And in the case of 3 generations, we can parameterize this with 15 unitary rotations. And then we can look at how it looks in the leptoquark couplings. And we take like this upper 3/6 block of this full leptonic mixing matrix at CKM. And we arrive at a semi-unitary rectangular matrix where this part here couples to the standard model quarks and leptons, and this part here couples to the standard model quarks and the vector-like leptons. So the full 3/6 matrix is semi-unitary, but the part which couples only to standard model fermions is not unitary anymore. And we can use this to get the desired LFE restructure and possibly be consistent with bounds from LFE decays. And this is how it looks if you put the matrix, for instance, in the C9, C10 Wilson coefficients. But depending on the SU2 representation of the vector-like states we add, they could induce non-universal Z to LL decays, or even lepton flavor violating Z to LL prime decays at tree level. And both those processes are very precisely measured quantities, and we don't want to mess with them. So this practically rules out every other representation than SU2 doublets, because they're the matrices exactly cancel that we still have universal standard model couplings to standard model fermions. So if we do this, we can explain the anomalies, but as we will see, we have very tight constraints from charge lepton flavor violation, like also from electric precision observables, and of course collider bound. The vector-like generations and get non-unitary mixing from that. And we take into account a lot of observables, of course, the anomalies we want to explain, but then also we don't want to mess with other data, which is consistent with the standard model. And there are also many LFE decays, which are important because most of them occur in tree level. So there's no loop suppression. And especially important is kaon decays to a muon electron, and also neutrinoless mu-E conversion in heavy nuclei. Yeah, and there's also, of course, a collider bound, which sets the mass scale for the leptoquark. And we choose it to be at 1.5 TeV. So yeah, here you can see the result of a random scan, like a Pullman's Monte Carlo. And I want to emphasize here that we take all standard model quark-lepton couplings into account. Like we don't set anything to 0 by hand, because if you don't impose a strict symmetry, you cannot do this in a gauge theory. And we take here 3 generations of vector-like leptons. So we have 12 mixing angles and we scan all of them. Here you can see the profile likelihood in terms of the leptoquark couplings I showed you before. And this one sigma shape looks pretty similar as the plot I showed you before. But with those many parameters, I mean, with 12 parameters, you can fit an elephant. Can you actually be predictive? So if you put the points I showed you earlier, which are here the yellow points, into perspective with the 2 most constraining observables, which are the kaon decays and mu-E conversion, you can see here in the blue points, which are the results of all the scan, which are like 10 to the 10 random samples. And all of them are ruled out by other LFE processes or by kaon decays and mu-E conversion, and only a small part of the parameter space survives. And if we now superimpose the future limits on mu-E conversion by the mu to E and Comet experiments, you can see that almost all of the future parameter space, that almost all of the preferred parameter space, like preferred by the B anomalies, will be probed in the near future. This is a very nice feature. Like those experiments can either discover this if they have a signal. It could be a strong hint for those leptoquark models. If they don't see it, it will be very tough to explain the B anomalies with it. Also, the Bell-2 experiment will improve sensitivities in B and in tau decays. And this is some ongoing work we are doing. I want to emphasize here on the process tau to phi mu, where Bell-2 has the same potential as a Comet in mu to E, which is shown here, to either rule out this model as an explanation for the B anomalies, or to see a signal if this model would be true. So those are very powerful probes in the near future. Okay, to conclude, the SM extensions with the V1 leptoquark offer a very good candidate to explain the B anomalies. But if you want to build a gauge model, you somehow need to get non-unitary couplings. And a possibility I showed you is to add 3 generations of vector-like leptons. But you need to comply with very strong constraints from LFE meson decays and CLFE observables. But what is nice is that a large region of the parameter space will be probed in the near future. So let me just say, stay tuned for the new results in B physics, which will be presented today and tomorrow. And thank you.
Okay, thank you very much for a nice presentation. So it's time for questions now. Okay, I can see a hand raised by Franco Romeo. Ooh, sorry, I don't see the first name.
Francesco.
Francesco.
Yes, thank you. Thank you for this nice talk. I wonder whether you can comment on the phenomenology of this particle and how would you suggest people at Atlas or CMS to look for it?
I mean, we are trying to explain RK star and RD star. So for the charge current, you need to somehow have an enhanced coupling either to C tau or to B tau or to both. So for the neutral current, you need to have B mu and S mu somewhat enhanced. So for this specific model, if you don't look at other leptoquark realizations, a strong hint would be to have like a B tau S tau final state. Or B tau B mu final state, because yeah, if you look at the combined explanations, you need to have somewhat enhanced couplings there. Like the B tau would be of order 1, and the B mu would be of order 0.2 roughly. And yeah, if you see a signal like this, this could be a strong hint towards this leptoquark.
Okay. Further questions? Okay, maybe I have one very fast one. I mean, if you have a significant mixing about your among your vector-like and standard leptons in the left-handed sector, don't you also produce a non-unitary neutral mixing matrix?
It depends on the specific model realization, on the scalar sector, how you generate neutrino masses actually.
Mm-hmm.
You, of course, just because you have vector-like doublets, you will have significant mixing in the neutrino sector. But depending on how you actually get the neutrino masses, this can be canceled with further neutral lepton states. So if you build a specific model, you need to take care of this.
I see, thank you. So I don't see any further question for Jonathan. So thank you again. And we should move on to another to the next speaker, which is Katarzyna Wichmann. Katarzyna, could you try to share your screen?
Yes. Can you hear me?
Yes, we can hear you. We
Okay.
can see you. Could you try to share?
Yes, let me try to share my talk. Can you see it now?
Yes, good. Could you try like to move on? Good, good.
Yeah, okay, very good.
Ready to go, please.
So good morning, everybody. My name is Katarzyna Wichmann, and I'm going to show you studies on contact interaction actually that happen at HERA and the ZEUS collaboration. So if you look at the general contact interaction, it's just point-like interaction here that you can interpret either as general contact interaction with those couplings or also as heavy quarks. With the effective leptoquark coupling shown in this way, or with the contact interaction coupling. And if you look at the diagram and ask yourself a question where you can actually find abundant electrons and quarks to study this, the answer to our question is HERA. I don't know how many of you remembers, but HERA was an EP collider in Hamburg in Germany and operated between 1992 and 2007. And it collided electrons or positrons with protons. It had two high energy colliding experiments, H1 and ZEUS. And what we try to look into is deep inelastic scattering. You see electron is scattering off quark, either exchanging gamma or Z boson, which we call neutral current, or exchanging W, which we called charge current. So deep inelastic scattering is the interaction that we will look into. So after many years of taking data, we actually combined the HERA inclusive cross sections from both experiments and H1 and ZEUS. And we started with around 3,000 data points, cross section data points, and we ended up in around 1,300. So what you can see on the figure is those are reduced cross sections for neutral current interaction as a function of Q square for various beams of X Bjorken, starting for very small and going up to 0.65. And you can see on this data both from electron proton and positron proton scattering here in different symbols and in different predictions. So you can see that it gives us huge phase space, and also we gained improved precision when we combine the data. First of all, we increase statistics, but we also have a better understanding of the systematics. And since those are there were two very different detectors, and the systematics and other uncertainties were completely independent, we have a cross calibration from those experiments. So what we will talk about today, it's this kind of data from HERA. So when you look at this diagram, of course, we scatter electron. However, we have a caveat in this interaction, because the quarks that we want to scatter of electrons don't come for free. They're actually bound in a proton, and it is a complicated object. And if you look at any cross-section, as you well know, for example, from LHC, in the interaction when you have proton, we also need the parton densities. And then this data, the HERA data is one of the main ingredients of every parton density. So if we assume, or if we hope that there is some beyond standard model signal hidden in HERA data, that of course it will bias and affect all the PDF fit, and it will result in a biased PDF. So we tried to look into this in detail, and if you look at this here on the plot, you see the analysis that we did first, looking in the quark radius in the same framework of contact interactions. And then if you look at the green curve, this is when we assume that there is that the quark radius is consistent with standard model. However, if you have a hypothesis and if you set limits that there might be some quark radius not according to standard model hidden there, that you see that you will actually overestimate your limits. So they will not be correct. So when we looked at this problem, we decided that the only really proper or stringent way to look for beyond the standard model interaction at HERA is do a simultaneous fit of HERA data and possible contribution from beyond the standard model. So we did this for the contact interaction because this was easily done from the theoretical point of view. So what we do, we fit simultaneously the parton densities and the contribution from contact interactions. So we use the prescription of those PDF fits from the HERA PDF 2.0 PDF determination. We use a tool that is called XVitter. This is the open source platform that it's very easy to use for this kind of studies. So we have standard model cross-section, and they are scaled with this ratio of interaction with standard model plus contact interaction and just standard model. So how you do those fits, you assume some kind of parametrization and the starting scale, and here you have this parametrization that we assumed. All these parameters in gray are fixed or calculated by the sum rules, and the parameters in pink are assumed to be the same, and the rest is fitted. So when you do this, you evolve your cross sections and your predictions using DGLAB equation. Here we did the analysis at the NLO, and then you get a fit that we called Zeus contact interaction PDF. You have it shown here. You see valence quarks, U and D. You see gluon 0. So you see there's not much difference. So if there are some contact interactions hidden, they are not big. And then just to show you how we calculate uncertainties of those PDFs, 0.0. We have first of all experimental uncertainties which take into account uncertainties of the data points, and this is realized on the plot in red. We use Hessian method for this, and we use conventional way of calculating data chi-square equals 1. And then we have two sets of uncertainties coming from different parametrization assumptions and also different model assumptions. They are mentioned here in the table for model in yellow and for parameterization in green. So the whole uncertainty comes from experimental plus model uncertainties. They are added in quadrature, and from parameterization, we just take the largest at each point, so an envelope. So those are uncertainties, and they're important to understand some of the results a little bit later. So here I just show you the contact interaction model that was studied in this analysis with different couplings and different helicities. So what you look at here, you can interpret it also as a heavy lepton quarks, and what we fit in together with PDF parameters are those couplings here for different models. There are 3 parameters in the fit. So when you look at those results, here you see the tables from the paper for various couplings and various models. And also in the so here is for, on the left is for general contact interaction, on the right are models on heavy lepton quarks. And what you see in the last column of each table, it's the data chi-square. So this is a difference of between the nominal fit when you don't assume any contact interaction in your fit, and a fit that assumes contact interaction on this particular model. So you see that usually it's very small difference. So the fit does not, if you add contact interaction, you don't gain anything. The data show you that there's no need for this addition. However, for one of the models, X6 here for general contact interaction, and for one of the lepton quark, S1L here, you can see they are marked in red. You can see that you actually get substantial improvements of the fit quality if you include this particular model in your QCD fit. And the larger is for this S1L lepton quarks. And actually, of course, this improvement gets a little bit smaller when you include all your model uncertainties. You see that they're quite large sometimes, but for this particular model, it persists even after including that. So then we looked how those fits compare. So if you look here in green, this is just a fit without any addition from standard model, from beyond the standard model, and this fit with the heavy lepton quark S1L is shown here in this gray, in this bluish dotted line. On top for neutral current E plus, and in bottom neutral current E minus. So you can see that in the top plot here, we can see that it differs from the standard model fit. And on the left, you have the same for the X6 general contact interaction model, where the difference is smaller, but still visible. So, okay, we don't really have, and well, here we cannot really see any mass peaks for lepton quarks, but we can set limits. And we used a technique using Monte Carlo replicas, and we derived them in frequentis approach. So how it works? So Monte Carlo replicas are calculated cross sections using this formula in the bottom, when you take into account for each replica with randomly generated here inclusion of systematic or statistical uncertainties. So you have the true value calculated. This is the value of your on your contact interaction coupling that you assume. And then you generate replicas with this particular value. For the plot you see on the left, it's this value was assumed 0, so no contact interaction. And then for each replica, we use around 3,000 replicas for each of those fits. You make the QCD fit, so PDF fit together with this coupling. You draw your distributions, and then you check how it corresponds to the coupling that was fitted from the data. So you see here, the coupling from the data was fitted around 3.13 GeV to -2. So then you can calculate the fraction of those fitted values of the couplings that is smaller or larger than couplings determined from the data, and you can use it to probe the probability. So this figure that I just showed you comes to this one point on top. So so for the true value of the coupling of 0, so we do it for very many points, and then to calculate 95 confidence level limit, we take those points around 5 and the probability close to 5 and fit it with this function. And we repeat it for all those values of true coupling that you see on the graph for each of the models with 3,000 replicas for each. So here are the results on the left on general contact interaction, on the left for heavy leptoquarks, and you can see expected and experimental in green and blue. And what is important is also experimental plus model uncertainties here. So you can see that they do actually affect the results. And in the bottom, you have some numbers for the masses of the leptoquarks that we can see if we assume the Yukawa coupling of 1. And when we compare it to LHC limits, only for 4 contact interaction models, there were studies at LHC. And for this, of course, you get better statistical sensitivity from the LHC. However, as I told you before, the systematic uncertainties from the proton PDFs that you have to use for those results can cause underestimation of the limits because of the possible bias in the PDFs. So this brings me to the last slide. So I showed you that we studied general contact interaction and heavy leptoquarks using the frequentist approach and Monte Carlo replicas, and we did it using the simultaneous QCD fit plus contact interaction with the fitting the PDFs. And actually, if you look at the probabilities of some of the models that I show you for contact interactions in the bottom and on the top and the leptoquarks on the bottom, some of those probabilities are below 1. And we actually, for those, have deviation from standard models around 2 to 4 sigma. And it is unlikely that those deviations are only from statistical fluctuations. However, if you take into account the modeling uncertainties that we got from other fits, those probabilities are around 5%. So it's much less statistically significant here. Thank you.
Okay, thank you very much, Katarzyna. We've got just time slot for questions. Ben, please.
Hi, thanks. I have a question. So there are indications for for some of the flavor anomalies that there's actually, it could be the 2nd or 3rd generation where you might see effects. Can you do this analysis? We're essentially looking at the strange quark PDF to do this. Is there a way you can, because then you would be able to you get a bit more access to sort of 2nd generation type couplings?
Yeah, Unfortunately, HERA data does not give us much information on the strange. We don't have it there. We have up and down quarks, so valence quarks and C quarks, and strange, unfortunately, is not really possible to look. We would need some extra information, for example, from LHC, from W and Z scattering, or W plus charm, or things like this. But with only HERA data, no. However, if there is a bigger project that also includes LHC data, then yes, that would be possible to look at things like this, I think. But this is, much bigger project, and going outside of the HERA data only. HERA data only does not give you information about strange quarks, unfortunately.
Okay, thank you very much, Katarzyna. We need to move on. So the next talk is by Christoph Alt, who will take us to South Dakota to nucleon decay searches with DUNE. Christoph, please share your slides.
Can you see my slides and can you hear me well?
Yes, we can. Yeah, you're on your full screen. Can you try to move on?
Sure. So I will be talking about nucleon decay searches with the Future Deep Underground Neutrino Experiment, or in short, DUNE. I will start my talk with a short motivation for nucleon decay searches and an introduction to the Deep Underground Neutrino Experiment before I continue with the simulation reconstruction of the signal and background samples and the analysis and results for this Monte Carlo sensitivity study. Throughout the presentation, you will find underlined text that links to references. So there are three main reasons to look for nucleon decay. The first reason is related to the observation that there's a clear dominance of matter over antimatter in today's universe. And now if you assume that matter and antimatter were created in equal amounts in the early universe, you need a process to create this asymmetry. And in 1967, Sakharov proposed baryogenesis, which requires a baryon number violating process to create the asymmetry. And nucleon decay is a promising candidate for this baryon number violating process. Now then in the 1970s, grand unified theories were developed that predict several nucleon decay channels, of which proton to positron and pi zero is the favored one. Also, nucleon decay poses the most promising test for grand unified theories because the unification scale is at energies that cannot be reached with accelerators we have. And the third reason to look for nucleon decay is supersymmetry. So supersymmetry, first of all, pushes the lifetimes predicted by grand unified theories to higher values, but it also opens up new decay channels through the exchange of supersymmetric particles. And for supersymmetric extensions of grand unified theories, the decay channel proton to antineutrino NK plus is the favorite decay mode, and this is the focus of this talk. Now, the lifetimes for these channels are predicted to be about 10 to the 34 to 10 to the 35 years. And this is exactly the problem why nucleon decay searches are so difficult. You need to basically look at a lot of protons for a long time in low background environments. And people have been looking for proton decay since several decades now. They haven't found any evidence, and best limits are currently set by Super Kamiokande. And you can see that the limit for proton to K plus and antineutrino is well below the predictions of supersymmetric theories. So the search for nucleon decay remains of great interest. Now we will be looking for these decays with DUNE. At the top you see a sketch of DUNE. It consists of a neutrino beam that is targeted at the near detector at Fermilab. And there's also far detector, which is located 1,300 kilometers downstream from the neutrino production point. DUNE has a rich physics program spanning from accelerator neutrinos to measure delta CP and neutrino mass hierarchy over nucleon decay, of course, supernova neutrinos and EMBAR oscillations, and many more. Now for nucleon decay searches, only the DUNE far detector is of interest, which is located in South Dakota at the Sanford Underground Research Facility. The far detector complex will consist of 4 single and dual phase liquid argon time projection chamber modules, each with a total mass of 17 kilotons. Now, these large TPCs have a resolution of about 5 millimeters, so they offer fine-grained imaging capability, which is very important for rare event searches. And they are located 1,500 meters underground in an old mine to shield against cosmic rays. And the first module will start taking data in the second half of the 2020s. And there's currently an R&D program underway with detectors that already have taken data, like the 35 tons and the 3x1x1. And the 2 protodunes at a kiloton scale that are still taking data today. So on this talk, I will present a study that was based on the single phase LAR TPC. And in the sketch, you can see the working principle. So what you have is you have charged particles inside the liquid argon that produce scintillation light and ionization charge. In case of nucleon decay searches, the scintillation light will give the trigger. And the ionization charge is then drifted by the means of an electric field towards 3 readout planes that are in the middle of this sketch. Now, each of these readout planes will record an independent projection of the event inside liquid argon, which you can see at the very right of the sketch. For a single phase, the maximum drift between the cathodes and the readout planes will be 3.6 meters, and there will actually be 150 independent TPCs inside one 17 kiloton module. The main difference between single and dual phase LAR TPCs is that in dual phase, the charge is drifted upwards instead of sidewise, and it is amplified in an argon gas layer. And the nucleon decay sensitivity study for dual phase is still in progress. So to determine the sensitivity of DUN to proton decay, we need both signal and background samples. And as I already said, I will focus on the decay mode, proton to antineutrino and K+. Now, since the proton decays inside an argon nucleus, it is not enough to just calculate the two-body decay of the proton, but one has to simulate the nuclear environment. So this consists of 3 processes. There's the nucleon density, the Fermi motion, and then finally the final state interactions of the kaon as it travels through the nucleus. All of these processes are simulated with Genie, which is an event generation toolkit developed for neutrino experiments. And at the bottom, you can see the kinetic energy distribution of the K+ from the proton decay. In black before FSI, so just after the proton decay. In red after the kaons leave the nucleus. And the dashed red histogram shows the kaons that have scattered. So you see that kaons that do scatter are shifted towards lower energies. And they will also come with additional neutrons or proton in the final state, while the kaons that do not scatter will not have additional particles outside the argon nucleus. So our signal sample is basically single kaons with a well-defined energy range, or single kaons accompanied by a neutron or proton. For the background, we consider atmospheric neutrinos. We simulate this with the Bartol neutrino flux and feed this into Genie to simulate cross-sections and the same nuclear model I've mentioned before. Now, there are various interactions between neutrinos and nuclei, and they produce different particles. You can see a non-exhaustive list here. 2 important things about these interactions is that most of them are below 1 GeV, so they are in the range of the signal sample and are therefore potential background. And also there are no single kaons produced in neutrino interactions on argon. So on the truth level, the background is always distinguishable from the signal. The table at the bottom shows the expected interactions in an exposure of 10 kiloton years. So this corresponds roughly to 1 year of data taking with one LAR TPC module. And we expect about a total of 3,000 events per year per module. Now, after the event generation, the particles are run through a validated simulation reconstruction chain. On the left, you can see a dual phase event display for proton decaying into kaon and antineutrino. I show a dual phase event display because I personally like it more, but the principle is the same for the single phase. So you have 2 projections in dual phase. On the left, you see the drift distance. So this is basically the distance to the readout planes. And on the x-axis, you can see the individual readout channels as they collect the ionization charge. The color scale is proportional to the ionization charges collected by each channel. The reconstruction is done in 3 steps: a simple hit finder for each channel, then a 2D pattern recognition which groups hits from the same particle, and the 3D reconstruction then matches the hit groups from the same particle across the readout views to get 3D objects on which the following analysis is then based on. So on the left, you see the K and tracking efficiency we currently have as a function of kinetic energy. And for intermediate energies, we have a quite low tracking efficiency. And by iScans, we have determined that we can improve the overall K tracking efficiency to a total of 80%. And I will get back to this when I show the final results in a couple of minutes. So the goal of the analysis is then to determine the lower limit on the proton lifetime in low background environments by trying to keep a high signal efficiency, of course, and reduce the background to 0. The strategy is to identify 3D tracks of the kaon and its decay products. For this, we define a particle ID variable, which takes into account the linear stopping power of the hits and the residual range of each hit. And you can see on the left that the discrimination power between kaons and muons is quite good, but there's a substantial overlap between kaons and protons. So this will lead to kaon-proton confusion. Now on the right, I show the same signal event I showed before and muon-neutrino charge current background event. So if you assume that in the background event, you misidentify the proton as a kaon, this looks quite similar to the signal event and is therefore a problem. However, there's a big difference between these 2 events, which is that the muon emerges from the kaon in the signal, while the muon and the proton share the same vertex in the background. So we can calculate the likelihood by walking along the proton and trying to determine if its starting or stopping point is connected to the muon to distinguish these background events from the signal. The final event classification is done in 2 steps. And we have 2 pre-selection cuts. And then we feed all the events with a training sample into a boosted decision tree. The most important input variables are listed here. It's of course the particle ID, the likelihoods. We also have convolutional neural network event display scores, and there are many other variables. On the left, you can see the discrimination power. We have chosen a working point where we have a signal efficiency of 15% at 1 background event in 1 megaton years. So this would correspond to 25 years of data taking with the whole Dune file detector complex. Now with the improved reconstruction, we believe that we can reach a signal efficiency of 30%. So we assume this when we calculate the sensitivity, and we get a result of 1.3 times 10 to the 34 years at 90% confidence level after an exposure of 400 kiloton years. So this is in the range of the prediction of supersymmetric theories. Now, we also looked at other decay modes, namely neutron to electron and K+. With the same analysis, we get also a sensitivity of 10 to the 34 years. And for proton to positron and pi0, we have done a Monte Carlo true study and smeared the energy. And the range we get is 0.9 to 1.1 times 10 to the 34 years for this decay mode, which is a favorite one by grand unified theories. So to summarize, nucleon decay searches can test grand unified theories, supersymmetry, and baryogenesis. Dune will be competitive for the favorite SUSY decay channel proton to antineutrino and K+. And Dune will, of course, complement the searches by Super and Hyperkamikando and UNO, with the big difference that Dune is the only experiment that offers high resolution images of the events, as you can see at the bottom again. Thank you very much.
Okay, thank you very much, Christoph. Time for questions. Maybe I have one. Actually, the K+ neutrino channel is your favorite one for obvious reasons. I mean, you like kaons in your apparatus. How about the other charge mesons which are kinematically available, like K star plus or rho plus, or perhaps pi plus? Can you say anything about the expected sensitivities here?
We have not done these studies yet. So I don't have a number for you because we haven't looked at these channels yet.
Okay, thank you. Actually, can I ask you about the background? I mean, what's the expected atmospheric muon flux through dune?
So you expect atmospheric neutrino?
A muon flux.
So muons are actually the the dominant background. So we have more muon neutrino interactions than other interactions almost combined. You can see this in the plot here.
Mm-hmm. Okay,
so half of the interactions are basically coming from muon neutrinos.
Yes. Okay, thank you very much.
Sure.
So if there are no further questions, I think it's time to move on. Thank you, Christoph. The next speaker is Mingang Zhao, who will take us to China and talk about baryon and lepton number violation searches at BEST3.
Hello, can you hear me?
Hello, loud and clear.
Okay, can you hear me?
Yes, we can hear you.
Okay. Good morning, everyone. This is Mingang Zhao on behalf of the BEST3 collaboration. My topic is baryon number violation and lepton number violation searches in charmonium decays at BEST3. Firstly, there is an introduction, and then I will introduce our two works. At last is a summary. Here is the bird view of the BPC2 and the BEST3 experiment. The yellow line stands for the LINAC. It is an electron-positron linear accelerator about 200 meters long. The electrons and the positrons are accelerated to 1.3 GeV and then injected to the storage ring, the red circle. The particles are further accelerated and accumulated and then annihilated here. This is our BEST3 detector. The BPC2 works 6 months as a collider and then 3 months as a synchrotron radiation facility. It is a well-designed high luminosity collider. The design luminosity was achieved at 2016. The BEST3 detector is a general purpose detector working at the BPC2. Its central mass energy is from 2 to 4.6 GeV. As is shown in the profile, the detector is composed from inside to outside. At first, a beam pipe, then a mandrift chamber with momentum resolution of less than 5%. And then is a time of flight counter with a time resolution of 80 picosecond for barrel region. For uncap region, it's 70 picosecond. Then there is an electromagnetic calorimeter. Its energy resolution is 2.5% at 1 GeV. The pink grid is a superconductor solenoid to provide a magnetic field of 1 T. And finally, there is a muon detection system. Its space resolution in alpha direction is about 15 millimeter and 70 millimeter in the Z direction. There are about 500 members in the BEST3 collaboration. They are from 76 institutes of 15 countries. Here is my university, the Nankai University. We have collected the world's largest charmonium datasets, which are directly produced from E+E minus clearance at several energy points. Especially, we have 10 billion GSI events. Based on this data sample, many rare and standard model forbidden decays of GSI can be investigated in the highest precision. So why we are interested in the baryon number violation? We know the fact of the asymmetry of the matter and the antimatter. It is a big problem in the current universe and its evolution. To give an explanation, Sakharov pointed that the baryon number should be violated together with the C and the CP violation. As is well known, the CP violation has been discovered and precisely tested in decays, both in theory and experiments. However, the established CP violation are not enough to address the current asymmetry of matter and antimatter. So many theories suggested even if there is a small amount of baryon number violation, it would have a major consequences on the evolution of the universe. So although baryon number violation has not been observed by any experiment, the searches would never stop. There are many theoretical models where BNV is allowed. For example, in the grand unified theory, proton can decay into several modes through leptoquarks, such as proton decays into a positron and a pi zero. Such kind of mechanism simultaneously violate baryon number and the lepton number while conserving the difference of them between the initial and the final state. So since there have been very precise constraints from the proton decay experiment, why we search it again with the collider? Because the searches with the collider experiment are complementary to those with specifically designed non-collider experiment. For example, there have been so many searches for dark sector particles, which supplement the dedicated direct detection experiment. And for the Mariana neutrino searching at flavor factory and the high energy frontiers are also complementary to the neutrinoless double beta decay experiment. So the two independent ways, I mean the collider and the non-collider experiment are supporting each other. So as is shown in the table, there have been many searches for baryon number violation in baryon decays as a collider experiment. They can provide different and complementary information for the proton decay experiment. However, there is no constraint of baryon number violation from quarkonium decays. So based on the 1.3 billion GSI events, we make the first search of GSI decays of lambda C and electron. The process can happen through the leptoquarks. So leptoquarks, as shown in this figure, this is one of the two diagrams through Y particle. Another one is through X particle. It is similar, so to save room, I not show here. And here is the anti-charm quark couples with a down type quark and a leptoquark Y. And the Y couples with an electron and an up quark. This is obviously baryon number violation and the lepton number violation process. While conserving their difference, we check the mass spectrum of PK pi for the signal. Here the black dots with arrows variables stand for data, and the blue histograms stand for signal monocolor. It is shown here to indicate the range of the possible signals. We can see there is no event survived in the signal region. The upper limit at 90% confidence level is calculated to be 6.9 times 10 to minus 8. This is the first baryon number violation searching in the charmonium decay. Okay, next work. The discoveries of the neutrino oscillation have made the N-bar oscillation to be quite plausible. If small neutrino masses are to be understood as a consequence of the seesaw mechanism, which can indicate the existence of this kind of interactions. Since 1980, there have been many experiments searching for the BNV through neutron and anti-neutron oscillation. However, there is few results from other baryon decays. In 2007, Luke pointed out that lambda bar oscillation may also exist. In 2010, Kang and Li gave a prospect of searching for lambda and lambda bar oscillation at base 3. In 2017, the LCB experiment presented a constraint from the cascade B0 and cascade B0 bar oscillation. So the theoretical advantage for lambda and lambda bar case is that there is a second generation quark, which can give further information compared with the result of proton decay. The lambda and the lambda bar oscillation can happen under the interaction of a 6 fermion operator, which could allow the baryon number violation while being consistent with the current limit of the proton lifetime. So suppose there is a beam of free lambda bar. If the lambda bar can oscillate into lambda, the probability of generating a lambda can be written as this equation, where the delta m sub lambda bar is the oscillation parameter, and the t is the lifetime, as a decay time. I'm sorry. Since there is no vortex detector at the base 3, so we can only measure the time integrated result. So the probability can be expressed as this fraction, where the p lambda is the oscillation rate and the tau sub lambda is the lifetime. Therefore, the oscillation parameter can be deduced as the oscillation rate over this constant. In this work, we can search for the oscillation signal in the decay of JIP psi decays to pk lambda bar. If the lambda bar can oscillate into a lambda, the final state would become pk lambda. Obviously, the oscillation rate can be calculated with this equation. The denominator is obtained from J psi decays to pk lambda bar, as shown in these diagrams. The left one is from the electromagnetic process, and the right one is from the strong process. The charges of the two protons are opposite. We call it the red sun channel. This is the decay without oscillation. The numerator can be obtained from the process of J psi decays to pk lambda, as shown in these two diagrams, where the lambda bar oscillates into lambda through the 6th fermion interaction. Here, the charges of the two protons are the same. We call it a Rankine channel. This is the decay with oscillation. In this ratio calculation, most of the systematic uncertainties are cancelled. So we can get the oscillation rate by comparing the event of these two channels. Okay, so based on the 1.3 billion G-psi event, we measure the ratio of the Rankine over Rankine channels. Here is the distribution. Here's the distribution for the Rankine and the Rankine. The lower plot is for Rankine, where the dots with error bars are from. The error bar is so small. Is obtained from the data, and the blue line is the fitting result. Here, the signal shape is obtained from the Monte Carlo simulated shape convoluted with a Gaussian function. And the background shape cannot see it, it's very small. Background shape is obtained from the inclusive Monte Carlo sample after excluding the Rankine event. The upper plot is for Rankine event in the signal region and the full span, where the dot with error bar is from data. The pink field histogram, which is normalized arbitrarily, is from simulated Rankine signal events. The arrow in the inside figure shows the edges of the signal window. We benefit from the nearly background-free result. The upper limit on the oscillation rate at 90% confidence level can be determined to be 4.4 times 10 to minus 6 level. Then the constraint of the oscillation parameter can be deduced as 3.8 times 10 to minus 15 MeV. Now let's summarize. With the world's largest threshold produced J-psi data, we present the first searching for J-psi decays to lambda C electron and the lambda bar oscillation. A better result for more decay channels based on 10 billion J-psi events are undergoing and are coming soon. Besides the new data taking plan and more charmonium data sets at other center of mass energies have been approved, better and more constraint on BNV processes can be expected in the future. So thank you very much.
Okay, thank you very much for the presentation. Time for questions. Okay, maybe I have one. Actually, you probably said it, but I didn't catch the point. So suppose you have an observable and kind of prominent signal of J psi to lambda CE minus, for instance. I didn't quite understand why you wouldn't have P decay in such a case, like proton decay. Maybe a bit fancy because you need like second generation quark in proton, but why this is not a problem?
I'm sorry, you're asking why there is not what?
I mean, suppose you really found J psi to lambda E minus at some really appreciable rates. So why don't you expect there, like, I mean, why doesn't it clash with proton decay searches? Like,
I mean, the why it doesn't compare with the proton decay?
No, yeah, okay. How does it compare with proton decay searches? I mean, with the null result of proton decay searches.
Okay. The our upper limit of this kind of decay is cannot be compared with the proton decay. Proton decay, for example, if we translate the upper limit on proton life to the branching fraction of proton decay, it is 10 to minus maybe 70, but not 70, 30, maybe 10 to minus 30 level. But our upper limit is only 10 to minus 8. So our searching, the meaning of our searching is a new searching in charmonium or a new searching in Pockonium. This is a different kind of searching besides the proton decay. Because in the proton decay there's the quarks for the first generation. So in our searching there's quarks of second generation.
Well, not necessarily, but okay. Let's maybe discuss this over MetaMost later.
Okay.
Any further urgent question, perhaps? Okay, if not, let's thank Min Gang again and move on to the next talk, which is going to be given by Kere Friedel.
Okay, thank you.
Thank you. On neutron anti-neutron oscillations.
Yes, hello. So I'm going to talk about the ability to probe baryogenesis using, like you said, neutron anti-neutron oscillation. And this is based on work done together with Julia Hartz and Chandan Hati. So as we heard before, and there's a problem with the matter asymmetry of the universe, and baryogenesis deals with the question of why matter exists. And the baryon asymmetry is then the amount of matter over the amount of antimatter in the universe. And for, like we also heard, for any mechanism to explain this, the mechanism needs to fulfill the 3 Sakharov conditions. So you need to have baryon number violation, CNCP violation, and out of equilibrium interactions. And all these 3 conditions are fulfilled in the standard model, but they lead to an asymmetry that's 9 orders of magnitude too small. So compared with the observation from Planck, we see that this cannot work. Therefore, we need beyond the standard model physics to explain the baryon asymmetry, and we ask ourselves how this baryogenesis can be probed experimentally. And to do this, we choose to search for a baryon number violation because it's a relatively model independent search and would provide a clear signal of beyond the standard model physics. And here I show 3 major ways to look for baryon number violation. So one is neutron anti-neutron oscillation, then we have proton decay and dinucleon decay. And our focus will be on these processes that violate baryon number by 2 units. So the neutron anti-neutron oscillation and the dinucleon decay, with an emphasis on the oscillation. And in any model that can explain the baryon number violation, we then say that it can be connected to the CNCP to also generate the baryon asymmetry. So the neutron anti-neutron oscillation experimental program is seeing some, it has some exciting future prospects. So we have the upcoming experiments Dune and NN-bar, which aim to put more stringent limits on this. The current limits come from Super Kamiokande and ILL. So with this respect, it's an exciting time to study the neutron-antineutron oscillation. And there are more talks at this conference about the neutron-antineutron oscillation, so by Broussard, Hua, and Stasser. So to describe the oscillation, we first do it model independently in an effective field theory. So the neutron-antineutron oscillation can be realized by these 3-level dimension 9 operators in 2 possible topologies. So one where you have a Majorana fermion in the middle, and one where you have a vertex with 3 bosons, which is the topology that we've chosen to study, but there are several works looking at the first topology. Now, in the EFT, we describe the Lagrangian as sum of operators with Wilson coefficients, where the Wilson coefficient goes as the 1 over the new physics scale to the power 5, where this lambda new physics scale encodes all the effects of heavy new physics. And there are several operators describing the different chiralities of the outer fermions, and as an example here, we choose to study the operator 1, where all the fermions are right-handed. And in this setup, we can connect it to this inverse tau, the oscillation time of the neutrons. And already in this EFT setup, we can get an idea of the effect of baryogenesis via the so-called washout. So if a baryon asymmetry is created at a high scale, it can later be washed out by a B-violating process. So in many models, you first generate an asymmetry at a higher scale, then some processes from the new theory are still active that violate the baryon number, and they can wash out the asymmetry, so reduce the asymmetry that you produce. And the effect of this can be estimated by comparing the width of the baryon number process, the gamma, to the Hubble rate. And the width of the process goes as the square of 1 over the new physics scale to the 5. So by picking some new physics scale, we can see by comparing the gamma to the H at which temperature this ratio falls below 1, and at that temperature the washout ceases to be effective. And we see for different scales it happens at different temperatures, but what we can see already here is that it does not happen. It does not wash out indefinitely, and therefore it can be interesting to further study these kinds of models. So to complete our EFT in a UV setup, we choose to study here diquarks. Now diquarks, these diquarks that we include here are scalar objects that are either color sextets or anti-triplets. They are SU2 singlets, and they have a hypercharge and they have a baryon number. So we have here 2 fields, the diquarks, and the XDD couples the 2 right-handed down type quarks, and the XUD couples to a right-handed up type quark and a right-handed down type quark. And we include also a vertex between the 2 diquarks with a mass dimension 1 coupling here that breaks that violates the baryon number. So it's really this 3 scalar vertex that violates the baryon number. And you see here, we realized the topology 2 earlier with the diquarks. So this diagram mediates the neutron-antineutron oscillation. And in this setup, you could also generate an asymmetry via the decays of the XTD. And the CPA violation here occurs with the interference of this loop diagram with the 3-level diagram. And these diquarks are very common in grand unified theories also. So, and furthermore, the diquarks can mediate the dinucleon decay. So what's shown here in this complicated diagram is a 2-loop diagram that mediates the neutron decay or the dinucleon decay 2 neutrons into 2 pi zeros. And we see here that with these W boson loops, the quarks are converted to the 3rd generation quarks. So in the case that the diquarks couple more strongly to the 3rd generation, the dinucleon decay can occur at 2 loop, but the neutron-neutron oscillation can only occur at 3 loops. So therefore, the 2 different experiments are useful as 2 different probes in this way. And to the right here, we see that in this diagram, with the current limits on this specific dinucleon decay, the parameter space is already being explored here for TeV masses and couplings of order 1. So this is indeed interesting. Furthermore, the diquarks can be searched for at the LHC. So the LHC also mainly puts constraints on the diquarks to the 3rd generation quarks. And the LHC is probing masses of the die quarks on the same mass range, so 5 to 10 TeV range. And it's a very good complementarity to the B violating searches, because at the LHC, you're searching for the particles themselves mainly, while in the neutron-neutron oscillation and the dinucleon decay, what you would see is the B violating process itself. So the complementarity between the two methods can be useful to really put constraints on the baryogenesis. And if you remember in the Lagrangian we had earlier, we had this FUD coupling constant that couples the XUD diquark to a U quark and a D quark. And based on the LHC center of mass energy 8 TeV data, for a coupling of 1, the masses of XUD below 5.4 TeV are disfavored. And for a smaller coupling, some smaller mass is disfavored. And so this can then be updated, of course, to the more recent data. And here you see the kind of mass range that you're probing at the LHC. So therefore, we are interested mainly in when if a signal is seen at the LHC, we're interested mainly in this kind of a mass range for the MXUD. Now, to generate actually the asymmetry in this setup, we study what's called the Boltzmann equation here. So the first term here with the epsilon CP asymmetry and the D that encodes the decay is the term that drives the asymmetry generation. So you see it's multiplied by the difference in the number density of the XDD from the equilibrium. So we can see in this equation the Sakharov condition that you need out of equilibrium decays. And with a minus sign in the second term here is the washout. So because of the minus sign, it simply removes the asymmetry. And the W here is related to the gamma over H, which we estimated earlier. And in our setup, there are several washout diagrams. So there are multiple S-channel and T-channel scatterings with any of the diquarks mediating the scattering. And the most dominant washout is the inverse decay. So when two XUDs fuse to become a XDD. And for the generation of the asymmetry, we have the loop decay of the XDD, interference with the tree level, trinity asymmetry. And already at this point, again, we can look at the washout. So again, we compare the decay width over the Hubble rate, and we again find that at some temperature in 2 different mass regimes, we cease to wash out. So this is in agreement with the EFT approach, and this tells us that it might be possible to actually generate an asymmetry in this setup. And here we're using a benchmark point of mass, XUD mass of 5 TeV. And we study these 2 different completely different scenarios. So once a scenario is interesting where the XDD is of a similar mass. And with respect to guts, it's also interesting to study the case where the XDD is a really high scale. So here we put it to 10 to the 11 TeV. And for high scale baryogenesis then, to actually calculate the final asymmetry, we find it here in the contour plot where on the x-axis we have the mass of the XUD, sorry, and on the y-axis we have the couplings. So here we put the FDD, the couplings of the DD and the UD to be the same. And if you remember, the observed asymmetry was 10 to the minus 10 approximately. So in white here you see the correctly generated observed asymmetry for an epsilon equal to 1. So for a smaller CP asymmetry, you would be somewhere in the red range. And we see from the blue lines that the neutron-antineutron oscillation experiments are already probing this parameter space. And with the dune and the N bar, they will go even deeper. So for this reason, it's interesting to study this. And a signal at the dune and N bar would really say something about the high-scale baryogenesis. Now for TeV scale baryogenesis, where the XDD has a smaller mass, the observable dinucleon decay rate requires the couplings to be large, and therefore the washout will be too strong, leading to an underabundance. And therefore, an observation of a dinucleon decay can be used to rule out TeV scale baryogenesis. But for smaller couplings, the baryogenesis can still work. Like we see here for small couplings on the y-axis of the FDD coupling, here in this plot we have put the FUD coupling to 1, such that the LHC will disfavor this area. If you remember, masses of smaller than 5.4 TeV was disfavored by the LHC in this setup. And again, we put the epsilon equal to 1 as a showcase scenario. And in the blue lines here for different values of the lambda coupling, so the strength of this tri-scalar coupling, in blue, you see where you generate a large asymmetry, or the correct asymmetry, the observed asymmetry. Yeah. So the LHC is also probing these kinds of feasible setups. So to conclude, we found that the interplay of diquark searches at the LHC with these B violation probes have excellent prospects to probe baryogenesis. And there are the high scale baryogenesis and the TV scale baryogenesis can both be, we can get some information about these setups from the dinucleon decay signal or a neutron-antineutron oscillation signal. And there are bright experimental future prospects at these Dune and Ennebar, and therefore it's timely to study the neutron-antineutron oscillation. So thank you.
Okay, thank you very much, Karev, for a nice presentation. It's time for questions now. Raise your hands in Zoom, please. Okay, maybe I have a very naive question. I mean, did I understand it correctly that your new source of CP violation is in the Yukawa couplings of your X fields, right?
So the CP violation is in the interference of the loop decay of the XTD with the tree level decay, yes.
Yes, yes. And I mean, do you produce non-zero B minus L by this mechanism? In other words, I mean, is this robust with respect to the Svaleron transition?
So the Svaleron conserves B minus L, but then I named this where is it? Yeah, here you see the subscript B minus L on the V here. So this is a new vacuum expectation value that breaks the B minus L. So since it only breaks the baryon number, it does not affect the lepton number. So in that way, it's B minus L violating.
Okay,
yes.
Robust. Thank you. Other questions? Comments? Okay, the discussion may continue on Mattermost. So let's thank Kare again, and it's time to move on and change the gears from baryon number to lepton flavor violation, actually. That will be reported on by Francesco Tenchini. Francesco.
Yeah, and I'll share the screen. Do you see it?
Looks fine, yes.
Okay, perfect. So today I will be presenting the first results and prospects for a study of for a search on lepton flavor violation in the tau to lepton plus invisible channel at Bell2. And this is essentially a search for a two-body decay where what we call alpha is an unobserved particle, which we detect by seeing some missing energy. And this is something that is not present in the standard model, but appears in several new physics models, for example, as a some kind of Goldstone boson. And the way we will be approaching this will be as a model-independent search. So we are making some minimal assumption on the nature of alpha, but we don't stick to any particular model. And what we will be presenting here will be some preliminary MC studies. We'll provide an estimate and some projections for what we can achieve for an actual tau to electron alpha channel measurement at Bell2. So the previous searches on this were done first at Mark III, then at Argus. And here they studied the lepton momentum in the rest frame of the tau, where you can see it as a sort of peak in the kinematics against the standard model background, which is tau to lepton neutrino. And this was done with the last measurement at Argus about half an inverse femtobarn Now, recently, Bell 2 has started operating as SuperCAC-V. This is a new facility aimed at studying beyond the standard model physics at the intensity frontier. So B, D, and tau decays. It's an asymmetric electron-positron collider, and it aims at collecting about 50 inverse autobarns of collision data, which is 50 times more than its predecessor, Bell. And it's a major upgrade of the accelerator with 30 times the design luminosity. This is just a sketch of the Bell 2 detector. It's a general purpose spectrometer, and it's very useful for this kind of searches because it's got a large solid angle coverage, so it's very hermetic, and is very good for this kind of studies with missing particles. Now, this is what is called a B factory, but is also a tau factory, since the production cross-section for tau pairs is close to the one for BB bar pairs. And historically, these kind of B factories have produced a variety of very interesting results in the last 2 decades. As you can see, we've reached about 74 inverse femtobars of total integrated luminosity collected, in particular during the data taking period in this year, which has been so far quite successful. And half of this has been reprocessed for analysis. So we are quickly ramping up to a state where we can actually reach competitive levels for physics discoveries of various kinds in this field. So how do we study for this? How do we search for this kind of decay? What we do is we study this, what we call the 3x1 prong decay topology, which means that we request that we have exactly 4 good tracks. One of them is a tau2 electron alpha. The other is a tag, which is tau2 3 pions. And then we use the thrust vector, which is given by maximizing this quantity here, and essentially describes the directionality of the decay, to define 2 hemispheres in which the 4 tracks must be, 1 on one side and 3 on the other. The dominant background here is the irreducible tau2 electron nu, which is not, as I said, it's irreducible. So we we cannot remove it, but we also, since we don't know, we make no assumption on the alpha. We don't know the mass of the alpha, so we don't have any specific kinematic region where the electron kinematics should lay. So the only way to optimize these studies by optimizing for the standard model decay. In other words, what we will be doing for background suppression will be rejecting all the other backgrounds, which are tau-taus, which are we do not decay in this topology, BB bar decays, QQ bar, and the various lepton pair production and photon fusion backgrounds. This is the first preselection is done by requesting a vertex fit on the 3-prong tag, and by vetoing any decay where pions and gammas appear, which heavily suppresses beam background and in particular QQ bar decays. Then we perform a further background suppression by studying 3 quantities: the thrust, the visible energy in the center of mass, and the invariant mass of the 3-pi system. And we optimize this by using a cut-based selection, using this figure of merit here, where S is the yield of the standard model channel, and we obtain these cuts here, which are shown also on the bottom plots. Here in the top, you see the distributions before the cuts, and in the bottom after the cuts with the cuts included. Then comes a conceptual problem. We want to study the kinematics in the rest frame of the tau, where you would have a single, essentially monochromatic peak for the electron, because it's a two-body decay. The problem is we need to boost to the tau frame, and we do not know that, because the only signal that comes from the tau is this electron. So what we need to is to approximate this frame by making some assumptions. Here we use two methods, and we try both of them. One assumption that we make is that the energy of the tau is the half of the beam energy. Then there's the so-called Argus method, which is what was used at Argus in the last measurement for this channel, where we assume that we take the momentum of the 3-pion system on the tag side, and we assume that the signal tau goes in the opposite direction. And then there is we can alternately assume that the tau flies in the direction of the thrust vector. You can see here the distributions for a standard model in red, background in blue, and two select cases for different masses of the alpha. And you can see that you can see some well-defined peaks for our signals here. The way we will doing this study will be by doing a template-based approach, where we fit the data with, or in this case, pseudo data with the templates obtained from Monte Carlo, and we will normalize using the standard model channel and try to extract this parameter of interest, which is the ratio of the branching fraction, which can be modeled as this formula here, as a linear sum of the templates where other parameters are treated as nuisance parameters. And the way we do this is using a frequentist profile likelihood method here, where we define the confidence level here for the signal as the ratio of signal plus background over background. And this is described here. This is basically what is provided in the RUStats package. And here we will be looking for a 95% confidence level upper limit. We are also developing an alternative test using a Bayesian approach, but it's not quite ready, so we're not presenting it today. And what we say, as I said again, what we present here is a preliminary MC study. We assume 25 inverse femtobarns of Bell2 data under current data taking conditions, and we do this by taking the standard model Monte Carlo 10 inverse femtobarn of Monte Carlo, selecting 25 at random to treat as pseudo data, and then use the rest to model templates. And for the signal, we generate events where the tau2e alpha decays using a phase space model. The tag side decays according to standard model, and this also used for different alpha masses to model templates. And we test both pseudo frame approximations. And this is what we get as projections. This is the upper limit provided for the ratio of the branching fractions. And as you can see, at this stage, no systematics are taken into account, and we're working into incorporating them. As you can see, the projection so far seems quite promising. We are looking at around almost 1 order of magnitude improvement compared to the previous Argus upper limit. And these plots are detailed in this note here, which is public, and if you download the PDF of this presentation, click it. It's a hot link, and you can check it out. And what are the future developments for this? So far, we established a framework for this tau2 electron alpha search. We have preliminary estimates for this upper limit. Then next steps will be to incorporate systematic uncertainties, in cross-check with these upper limits with also a Bayesian approach. And also, if possible, we are also on parallel developing new techniques to maybe improve this tau rest frame approximation in order to perhaps better have more distinct signals, which may improve the fit. And of course, the final analysis will incorporate the tau2 mu alpha channel. When we started setting up this, the muon ID was not quite at the stage where we trusted it to perform the way we needed it to in order to do the first study. So to conclude, BEL2 has shown potential to improve this measurement significantly, and this will provide interesting constraints to new physics models. And stay tuned for more. And thank you for your attention.
Okay, thank you very much, Francesco, for a nice talk. So it's time for questions now. Raise your hands through Zoom. I don't see any, but maybe I have a very brief and simple question for you. I mean, when do you expect the phase 3 data to become available for your type of analysis?
So in principle, we already have, as I mentioned, actually more data than the assumption that we made in this study. We simply didn't. We are not at a stage with the systematics estimation and the other upper limit measurement with Bayesian approach, where we could confidently converge on an actual database, an actual measurement in time for this conference. But I mean, the data is available, so we are proceeding with this, and hopefully within months we should be able to produce a first results. I cannot say if it will be with this amount of data or a bit more, since by the time we will have probably reprocessed also the rest. And that's okay. That's still open.
Thank you. Other questions? Comments? Okay, I don't see any. So, I mean, if there was anything to Francesco, please use the MetaMost Track 3 chat. And for us, it's time to move to the last talk of this session. We'll be looking into the dark side of the universe with Xavier Cid-Vidal.
Hello.
Hello.
Okay, let me share my screen.
Sure.
Can you see it?
Yes, we can. Could you go full screen?
Yeah. Okay. So can you see my full screen now?
Perfect.
Yeah, okay. So yeah, thanks so much for giving me the chance of being here. It's a pleasure to be in Prague, even virtually. So I'm going to present today the searches that we have done for dark photons at HCB. I'm also including a new result that is not exactly dark photons, but which includes a very similar final state. So first of all, let me start introducing what are dark photons and what are dark sectors in general. So the idea is more or less explained by this cartoon here. So you've got different paradigms to address the standard model problems. You have the well-known WIMP paradigm, where you have and were somehow the same theoretical framework, the standard model, plus extended sectors with more particles, and SUSY, for instance, would fall in this paradigm. And then you've got this new idea where you would have somehow two decoupled sectors, the standard model and a dark sector, where you would have somehow completely independent particles and fields. And then you would have the chance to connect both sectors through portals, and this connection is in general weak, and it has to be done through loops. So you've got different types of portals of this kind, and these portals somehow express themselves as via mediators. You've got the Higgs portal, the vector portal, the neutrino portal, and the action portal. And the nice thing for LHCb is that we are sensitive to them all. But today I'm just going to focus mainly in the vector portal. And the most spectacular example of this is the dark photon. So the idea is that you would have a particle in the dark sector that would more or less play the same role as the photon in the standard model. This is why we call it dark photon. And there's a coupling between the standard model photon and the dark sector photon via kinetic mixing. So this is a loop. So this is via loop. So this means that you have essentially a small coupling. So you've got you need a lot of data to find these dark photons. So the signature you would have would be a resonance in the either prompt or displace. It depends on the type of coupling, the electron spectrum. So the dark photon would essentially decay to E or mu, for example. And since this theory has emerged, there has been a worldwide effort to try to find these particles at the LHC, but also at big factories or fixed target experiments. So in this cartoon here, you can see how the picture looked before LHCb started looking for this kind of particles. So in the x-axis, you've got the mass of the dark photon, and in the y-axis, you've got this epsilon parameter, which corresponds essentially to the coupling between the dark photon and the standard model photon. So at LHCb, between 4 and 5 years ago, there were two proposals to search for dark photons. One would be the immune direct search, and this is what I'm going to cover today. And then there's also this other idea to search for A prime to E plus E minus through charm decays. And this has not yet been done, but it will be done in the years to come. So just before going into the details of the analysis, let me just give a couple of experimental generic considerations. And one is that LHCb is well known as a flavor physics experiment. And the reason for this is that, in principle, we collect less integrated luminosity than Atlas and CMS, around a factor of 15 less, and the acceptance is limited for several searches. So in this cartoon here, I'm showing what CMS and LHCb would look like if they were in the same cavern. Well, this is not to scale, so LHCb would be a bit smaller, but in any case, here you can see that CMS has sort of a 4 pi coverage, while LHCb is a forward detector. And both factors combined mean that, in principle, we can detect less of these new particles. But on the other hand, we've got triggers that are way softer. So, for instance, we can trigger the touch dimuons with very soft PT cuts, very good verticing, PID, momentum resolution. So this compensates in big regions, in big parts of the parameter space. The other disadvantages, so that means that we can be sensitive and we can be complementary to Atlas and CMS for some cases. Just one more word about the trigger, which is very important for this analysis. So in round 2, we had the second level of the software trigger that was very close to offline. So you've got in the left-hand side the usual trigger scheme for LHC experiments. So you had the levels, hardware level 0 trigger and then software level triggers. But the big advantage for us is that, as I was saying, for this second level of the software trigger, everything was almost similar to offline. So because we were running online calibration and alignment of the detector, so that means that we can essentially achieve offline quality reconstruction at the trigger level. So for instance, our dark photon search was done based on HL2 objects. So this HLT2 is the second level of the HLT. And we had, for instance, no prescales on mu even for prompt dimuons down to threshold. so 210 MeVs. Just a word for the upgrade. So we are at the moment upgrading our detector, and from round 3 on, we will run essentially with no trigger, in the sense that we will have no hardware trigger. We will have only a software trigger, and in this software trigger, we will have, again, very close to offline quality reconstruction. So that means that essentially, we'll be able to perform our full physics program with no trigger. And this will be very beneficial for searches of this kind, and will also improve our prospects. Okay, now moving on to the searches for dark photons themselves. So as I said before, you can look for dark photons through a dimuon, so doing a bump hunt in the dimuon spectrum, and this is what we did in this case. So we used our full run-through data set. So this analysis updates previous search we had done only with 2016 data. So as I explained before, the A prime can be very light, and it can be produced essentially as a virtual photon. And a large fraction of these dark photons, if they are light, so below 10 GeV or so, are in the focal region, so very good for HCV and very soft in PT. So in the right-hand side, you've got a plot of the dimuon spectra that we got in this 2016 paper, where you can see that the dimuon spectra is composed essentially by real mu plus mu minus pairs produced either in Drell-Yan or light emission decays, or if not, in by background composed by heavy QCD, so BB bar pairs decay into dimuons, or even a small component from misidentified hadrons. So the analysis flow for us is more or less similar for prompt and display. So essentially what we do is we self-normalize to virtual photons decaying to mu plus mu minus, so essentially to Drell-Yan. And the reason for this is that in principle, this Drell-Yan to mu is indistinguishable kinematically from a real dark photon decay. So that makes our normalization easier. Then concerning the backgrounds for the prompt search, as I said a moment ago, you've got backgrounds from the hadron decays. So for those, you compute them using same sign muons, and you also do fits to the IPK square, since the muons from B decays tend to have larger IPK square. And then for the lighter case, so below 1 GeV, you tend to have more virtual photons from light hadron decays. So there you don't want to apply isolation, but above that, you apply isolation. Then for displaced, the backgrounds are more or less the same, but you also have K short to pi pi, where both pions are misidentified as muons. And then you've got material interactions, so essentially cases in which another particle hits the material and through an elastic interaction produces a mu plus mu minus pair. But we've got the vectors for this all. So it's all summarized in the cartoon I got in the right-hand side bottom plot, both for the prompt and the displays case. So the signature is a bit different, but the idea is more or less the same. So these are the results that we got. So in the left-hand side, we've got the prompt results, where you can see the current update, the old 2016 data, and the results from other experiments. And as you can see, our results are well best, essentially below 1 GeV, above 10 GeV more or less. I should say that there's a new result from CMS covering the same type of model. So here you can see very nicely the complementarity between both experiments. So LHCb dominates between 10 and 15 GeV more or less, but then above that, CMS starts to be better. This was presented on Tuesday in another talk. Then for in the displays case, again, you can see the exclusion by LHCb. And as you can see now, we are able to exclude a much larger region compared to the previous result in 2016. So in this plot, essentially what we are showing is the regions. So in blue, you've got the regions where you can exclude, sorry, the observed is smaller than the expected. So that means that you can essentially exclude those regions. The rest are regions that we hope to exclude in the near future with the forthcoming data. So this is the whole picture again. So as you can see, now that the LHCb has started looking for dark photons, we have well, the parameter space has become more constrained, and we will be able to do much better in the forthcoming years. So actually, I got this plot here. So this was part of the Beyond the Standard Model Physics at LHC report that was submitted around a year ago. And this is what we expect to exclude with our full data sets. So you've got both the mu plus mu minus and e plus mu minus searches. And as you can see, we will be able to exclude most of the parameter space below 1 GV and a large fraction of it below 10 GV or so. I should highlight that this plot was part of the 10-page summary that was submitted to the European Strategy for Particle Physics. So I think this is a very important channel. Okay, so as I promised at the beginning, we've got also a new result, and that came out just a few weeks ago. And this is addressing non-minimal searches. So the thing is that, well, in this specific case, as I explained, we were looking for DAC photons, which have a specific signature where, for instance, you can isolate your signal above 1 GV, or you require your DAC photon to be pointing back to the parameter vertex in case it's displaced. But there are other models where you have mu plus mu minus, which produce similar topologies, but not exactly the same. So what we did is to perform a model-independent search and provide a few examples of interpretations of those. So we've got 4 different categories, inclusive or displaced, and you can also consider the associated production with B-jets, which appears in several models as well, and even other more strange cases like having not the mu plus mu minus not pointing back to the primary vertex, or even having non-zero natural widths, and I will explain the results in a moment. So the idea is essentially the same as before, but now instead of normalizing to Drell-Yan production, now you do a mapping of the efficiency in terms of the lifetime and PT, and then you can exclude different regions depending on those. So it's somehow a more complete search that can be used for interpretation in any model that you have that produces mu plus mu minus resonances. So for instance, these are the results for the prompt non-minimal case. So these are the low mass upper limits at 90% confidence level on the cross-section of any resonance to mu plus mu minus. So you've got the inclusive and the beauty-associated cases. And the gray regions are those where we couldn't set up any limit, essentially because we expected almost no signal, or because you've got standard model resonances that dominate there. For instance, the upsilons at around 10 GV. And yeah, we're able to exclude down to 1 inverse femtobarn in some of the regions of the in PT and mass of this resonance. So this was for light resonance below 10 GV, then above 10 GV, these are the results. And again, here we cover the inclusive and beauty-associated cases. And the new thing here is that we also cover non-negligible natural widths. So natural widths up to the level of, well, few dozens of MeV. And this is what you see in the y-axis in these plots. And again, here we are able to cover or to limit cross-sections down to the level of 1 femtobarn. Of course, as soon as you start assuming large natural widths, then the limit is worse, as one would expect. I should also say that this search, as you may imagine, is sensitive to the excess that CMS had found in the mu plus mu minus spectra in association with two B-jets. And this is what I'm showing in this plot here. So we did this specific search a la CMS, where you look for 2 jets plus the immune resonance, and we looked into the mass region where the excess in CMS appeared, but we have no evidence at all. We even have downwards fluctuation here. So yeah, we cannot confirm at all the excess that CMS have seen with their round 1 data. Then moving on to the displaced searches. So you've got, again, inclusive and beauty associated, and here we only cover masses below 3 GV. And yeah, again, we are able to exclude down to 1 inverse femtobarn in some cases. And this gray region here corresponds to the K-short to pi region, where essentially you've got too many background to exclude anything. So I'm giving now a couple of examples of interpretation. So for instance, in the top plot, you've got the the 2HDM, or a kind of a type of 2HDM scenario. And what you've got in the y-axis is the mixing angle between the Higgs and this new particle, and in the x-axis you've got the mass. And as you can see, we are able to exclude. So we have world-best exclusions in several regions. So we've got the results in this search that I just presented, and there was also another search done at around 10 GeV, where we were looking at the upsilon mass region. So we were even able to look between the upsilon resonances, which is quite remarkable. So I have no time to cover this, but this will be shown at another LHCb talk later today by Elena Dall'Occo. And then we've got the hidden valley scenario. So this displays our photons, and this is I'm showing the exclusion here in the gamma set, the hidden valley set kinetic mixing, and you can look at the theoretical results for more details. So let me conclude now by saying that LHCb has now become one of the main players in the search for dark photons. So I just presented brand new results that produce world-best limits in several regions of the parameter space, and this will improve in the future. So we've got these new model-independent results as well, which cover different related signatures, and they are sensitive to a large number of models where these dimming resonances appear. And I think this is a perfect example of the LHCb potential to this type of physics. And let me conclude saying that LHCb can be really the new detector to directly discover BSM physics, so something similar to what ICHEP of Mathusla proposed, but with a big advantage that is already built. So I invite you to follow Elena's talk later today, which will show many more interesting results in this area. So thank you.
Okay, thank you very much, Javier, for this concluding talk of the first block today. It's time for questions. Raise your hands, please. So maybe I can have a very naive outsider question. I mean, if I'm not mistaken, you're looking for these dark photons with masses in, say, several tens MeV onwards, right? So relatively heavy objects. Mm-hmm. So I assume there are no cosmological bounds for these things.
I think if you start going down to smaller, to very small couplings or to larger masses, then you start having. So I mean, in the specific region where we are searching for, I think the cosmological bounds are weak in there. Mm-hmm. You have to go to other couplings or masses, I think.
Okay. Yeah, that's what I would expect indeed. Yes. Actually, maybe one more question. That's very like a speculation. I mean, is anybody entertaining those scenarios in a way that if you are supposed to have such a relatively heavy dark sector gauge boson, it may be associated to a spontaneous symmetry breaking in a dark sector, and there can be a monopole in the dark sector. So, I mean, are there any kind of options for like searches for both, or just like speculating?
You want to search for that photon in association with a monopole, or
I mean, or for those types of monopoles which would be likely millicharge or whatever.
I mean, not at LHCb. So there's, for instance, model that sits in the same experimental area as LHCb, so it's around essentially our vertex locator that is looking for monopoles. It might be interesting to try to look for stuff in coincidence, but I'm not sure if this is how feasible that is technologically.
Yeah, I didn't mean like a coincidence signal. It's more like a very exotic type of monopoles.
I'm not familiar. I know Model is doing these kind of things, and I also know Atlas and CMS are looking for monopoles, but I'm not sure if they are the same kind that you're proposing here, to be honest. So.
Okay, if there are no more questions, let me conclude this very nice session. I would like to thank all speakers for their beautiful talks, all attendees for their presence, and I propose to reconvene with a new chair, which is going to be Yu Nakahama for you for the next block. I propose to reconvene at 10:50. And I would like to encourage those speakers of the second block which did not yet test their equipment to do it so during the coffee break. Thank you very much. Okay, we have Gui Lin.
Yes.
Could you please try sharing your screen?
Okay. So is the screen okay?
Yeah, we see a full screen slide, and it's there are transitions. Yeah, good, perfect.
Okay, good. So the sound is also okay?
Yes, the sound is also okay.
Okay, great. Yeah, so I'll be the first speaker. Yes.
Yes, but please unshare now because
okay,
we
sure.
Also the others.
Okay, all right.
So the next one should be Ivania.
Yes. Can you hear me?
Yes, we can hear you perfectly. Could you go ahead with sharing, please?
Okay. It's okay?
Could you go full screen?
I'm full screen.
You're full screen. Can you try a transition? Perfect. Yeah, works for us. Great.
Okay.
Thank you. Please unshare.
Okay. Okay, I did it.
Good. Actually, I don't recall whether we did try with Federico.
Yeah, I think so.
Okay, fine. I think we did with Priyanka.
Yes.
And Martina. We did, I think. How about you, Elena? Could you remind me whether we did or did not try yet with you?
We did not try yet, so I can try to share now.
Go ahead.
Yeah. Can you see the screen?
Yes, we can see the screen. Could go full screen, please.
Yeah. Now?
Yes, we do. And could you try a transition because you're on Mac, right?
Yeah.
Good. Works.
Works. Okay, perfect.
We can hear you loud and clear.
Perfect. Great.
Who is the next one? Did we try with Javier? Or Denise?
I think they aren't connecting yet.
Yeah, I'm just looking for them indeed. They are not connected.
So hello, now I see the Javier is connecting. So maybe could you check the shared screen? Can you hear me okay? So we want to check if all the speakers check the shared screen. So now I see the Dennis and Javier. So maybe could you want to try that now? We'll start at the 10:50. So hello everyone. Now it's at the 10:50. So we'll start the second half of the today's session. So here we'll hear the two dark sister talks, followed by several exotic talks. So yeah, we start with the first speaker. So Gillian. So
Yes.
yeah. So could you start the shared screen? So our first speaker is Gideon Lin, who will be talking about the polarization effects in the search for the vector dark boson at the E plus E minus collider. So so you have the 12 minutes for a talk, followed by the 3 minutes for questions. And then here, in the when the 10 minutes passed, you will hear the bell, okay?
Okay.
Please start.
Okay, so thank you very much. I'm going to talk about polarization effect in the search for dark vector boson in E plus E minus colliders. So to save time, let's go to the Lagrangian here. So as you can see that the dark photon basically is the mixing between the dark boson mixed with the U1 hypercharged field. And so this induces an interaction between the dark photon with the standard fermion through electromagnetic current. And in this case, the neutral current interaction is suppressed. However, if the dark boson can mix with the Z boson through the mass mixing, then we can generate also the neutral current interaction between the dark boson and the standard model fermions. Therefore, combining the two interactions together, we can write down the dark boson interaction with standard model fermions with the two terms proportional to GV and the GA. Okay, so therefore, in the experimental search for ZD with the E plus E minus to ZD gamma, can one determine the relative strengths of this vector and actual vector couplings. And today I'm going to speak about the key is on the polarization of the ZD. Okay, so the first thing I'd like to emphasize is that when the E plus E minus energy is much greater than the dark boson mass, then the dark boson should be produced in only the transverse states. And this can be seen from the Ward-Takahashi identity because if you take the longitudinal polarization vector of the dark boson, and this longitudinal polarization vector can be approximated by the K1 mu over the MZD plus correction terms. And as we know that the K1 mu multiply with these two diagrams would give you 0 due to the Ward-Takahashi identity. Therefore, theoretically, we expect that the longitudinal contribution should be suppressed. And this can be demonstrated from the explicit calculation. So here I calculate the amplitude square for the E plus E minus to ZD gamma. And so this is the polarized amplitudes. So I have a plus Healy states, minus Healy states, and also longitudinal states. And here the theta is the direction, is the angle between the ZD and the E minus direction in the CM frame. So from this expression, you can see that the plus minus states are actually proportional to the S square, where the longitudinal only proportional to S. So we see the dominance of transverse states. And for cross section, one can simply take the amplitude square, multiply some prefactors, and you can get a polarized differential cross sections. And we can plot the polarized differential cross section. So we take an extreme V minus A coupling case and take the epsilon equal to, so this is a mixing parameter equal to 7 times 10 to the minus 4. So this is basically the current sensitivity by the Baba measurement with the 500 inverse Van der Waals data. And root S here is about to send a mass energy. Okay, and so you see that here, the black curve is the negative Healy states, and it dominates the so-called forward direction. And the red curve, which is a positive Healy states, it dominates the backward direction. And you see the longitudinal direction contribution given by the blue curve is very, very suppressed, as we can expect. However, once you increase your dark boson mass to be comparable to the root S, and what you see here is that the longitudinal contribution is no longer negligible. And more importantly, the helicity +1 and -1 state, these two transverse states actually, their distribution are getting close to each other, okay? Although we take extreme V minus A limit. So, so this is a distribution of the ZD production, the dark boson production direction distribution. And one can also analyze the so-called decay distribution from this dark boson. So we want to perform the so-called visible search. So this dark boson will decay to lepton pairs. So if you study the angular distribution of the decay, and you can see that this is a plus helicity plus state, helicity minus states. And once again, here the theta d, this is the so-called helicity angle of the lepton, which is the lepton direction in the ZD rest frame, and also the angle between this direction and the ZD boost direction. So here we can see that this rho is actually defined earlier, and the rho here is the so-called the parity violation parameters. Okay, so you can see that the angular distribution for the +1 decay and the -1 decay also differ by a minus sign. Is governed by the parity violation parameters. And the longitudinal states, the distribution is a proportion to sine square theta d, which is forward-backward symmetric, but for the transverse states, it's a forward-backward asymmetry. Okay, so so we see that there are so-called angular distributions for the ZD production and also angular distribution for the ZD decays. So one can actually combine these two distributions to form a double distribution. And so I have a d squared p, d kappa, d c. So the kappa is the cosine theta. And once again, the theta is the angle of the ZD of the dark boson with respect to the beam axis. And the theta d is the helicity angle of the leptons, okay, with respect to the dark boson boost direction. And one can write this double distribution into two terms. The first term is a Q0, and the second term is Q2. Q2 is a proportional to the rho square, proportional to the square of the parity violating parameters. And also Q2 has a characteristic that the Q2 actually is a proportional to the kappa times c. In other words, if the kappa c changes sign, then the Q2 term also changes sign. Okay, and so this is a use for our so-called dark boson search, because in this case, one can define the so-called asymmetry parameters, which is AEPN. And these asymmetry parameters is taking the difference between the signal events with the kappa c bigger than 0 minus the signal events with the kappa c less than 0. So if you take this difference divided by the sum, and you can see that these expressions actually proportional to the rho square. So it is the parity violating effects parameters which govern this asymmetry. Okay, and so so we can test the dependence of these symmetry parameters with our kinematic range. For example, if we fully integrate the c where cut the range for the theta, and you can see that when the cosine, the maximum of the cosine theta is taken to be 0.95 and the minimum to be minus 0.95, and you see that asymmetry parameters is given by these expressions. And you can see that the asymmetry parameters can reduce slightly if you have the kappa maximum to be 0.8. Okay. This is just a naive estimation, and we know that this parameter is to be calculated with the actual detector acceptance. And also we know that this asymmetry will be diluted by the QED background, because the QED background corresponding to the rho equal to 0, it does not have any parity violation effect. So there's a dilution effect. So the question finally is that how significant is this asymmetry statistically? Okay, so so let's go to the actual Bell detector angular coverage in order to calculate the asymmetry parameters in a more realistic settings. So, so this is the angular range for the Bell to calorimeter, the angular range for Bell to calorimeter, and also this is the range of the K-long muon detector angular coverage. And so you can actually get the so-called rapidity range for the photon, and also rapidity range of the photon and rapidity range of the muon, mu plus and mu minus. Okay, and so you just make this cut. Okay, so if you make this cut, and we find that the asymmetry parameter is actually equal to the following values. We take the two benchmark masses for the dark boson mass to be at the 0.5 GeV and 2 GeV. And we also choose two different sizes of the parity violation parameters. For the first case is when you have the so-called epsilon gamma mixing. So this is original so-called dark photon mixing. And this is so-called epsilon z induced by mass mixing. If these two parameters are identical, we have a rho equal to 1.74. So your asymmetry parameters is roughly 0.38, 0.36. And suppose you take an extreme V minus A case, that means that you take epsilon gamma equal to epsilon z times tangent theta 1 per angle, you have a rho equal to -2. And we know that these asymmetry parameters are only proportional to the rho square, so that the minus sign here is not important. So here you see that the maximum asymmetry parameters which reaches almost half. Okay, and so this is a calculation done by ICHEP. So we calculate the asymmetry parameters in Bell 2 detector and what these asymmetry parameters can help for our search. So for example, in Bell 2 or Baba, one search for the dark boson. And so if we just count the overall event axis, so the chi-square here equal to this form with the n is the observed event numbers, including signal and background, and W is expect background, which is B. And so one can easily obtain the detection significance to be S divided by square root B. However, if we consider divide events into the two different beams corresponding to kappa times C bigger than 0 and less than 0, and so we write a chi-square corresponding to events with these two beams. And so here the asymmetry parameters is equal to SA minus SB divided by SA plus SB. And so with this extra handle, actually we can enhance our detection significance in this way. So you see that it is not only S divided by square root B, but there's a square root 1 plus the asymmetry parameter square, okay? So this is the enhancement. And secondly, the second question we concern is that if we do observe the NA not equal to NB, of course, this is a signature of the so-called some scenario beyond so-called dark boson scenario. You have a vector coupling and also actual vector coupling. So statistically, when one can try to fit this case by the dark photon assumption and see how much the dark photon can be disfavored versus the so-called more general dark boson scenario. So you can calculate the minimum of this chi-square, and this minimum of this chi-square will happen at the WA equal to WB, okay? This has to be imposed for the dark photon scenario. And so the minimum chi-square will happen at both of this number equal to NA plus NB divided by 2. And so this chi-square will be found to be S squared divided by B times asymmetry parameter square. So therefore, one can conclude that the dark photon scenario is less favored by these significance. So it's S divided by square root B times the so-called the asymmetry parameters. Okay, so S divided by square root B is the overall detection significance. And these asymmetry parameters come in to tell us that how much dark photon scenario can be disfavored. Okay.
Sorry to interrupt a bit, but maybe you need to speed up. We have 1 minute, only 1 minute more for your talk session, including
Okay.
questions.
All right. So I'm going to finish up. So this is the number we have. Okay. So finally, I just present my conclusion. So here, the 5 sigma detection is our assumption. We assume that we can reach 5 sigma detection at the full integrated luminosity of Bell 2. If we divide by events by the 2 beams, and you can find that you can increase your detection significance to 5.3 sigma for rho equal to 1.74 and to 5.6 sigma for rho equal to 2. Okay, and the dark photon scenario can be disfavored by about 1.9 sigma if we have a rho equal to 1.74. For the extreme V minus A case, the dark photon scenario can be disfavored by 2.5 sigma. Thank you. That's all.
Yeah, thanks a lot for this nice talk. So maybe a quick question, if there is. It seems not already clear. So in that case, thanks the speaker. Thanks a lot the speaker again. So we move on to the next speaker.
Thank
Thanks.
you.
Thank you.
Okay, can I share my screen?
Yes, please. So our next speaker is Ibiana Majorana Villa. So we will be talking about an extensive study of dark matter in the singlet and triplet scotogenic model. So please go ahead. So maybe you need to try the full screen.
Okay, it's full. Yeah. I'm screen now. So I will present this study of the specific type of scotogenic model that I did in collaboration with Valentina Romeri, Laura Duarte, and Jose Valle at Valencia. The idea of this model is that we know that there are some open questions that exist because in physics, and the standard model cannot solve by itself. One of them are related to neutrino masses, that we know that neutrino have a mass that is different from 0, and there are many theoretical models trying to explain that. And we also know that at least 85% of the universe, of the matter of the universe, is dark. So there are many kind of scenarios and candidates of different type of particles to be a dark matter candidate. And in this work, we are focusing in a wind particle as a dark matter candidate in a freeze-out scenario for cold dark matter. We also know for recent measurement of dark matter abundance by Planck satellite that the dark matter abundance is this number that we can see here. So the scotogenic model is a model that is trying to explain these two open questions and generate neutrino masses at one loop level. Where the mediators are the new particles of the scalar sector that are introduced in this model. The idea of the scotogenic model was proposed by Ernest Mach first, and also the model presents a dark matter candidate that can be a scalar or a fermion. Also, the model adds an extra symmetry called the C2 symmetry in order to stabilize the dark matter candidate. So it has been generalized in many ways. We study one of them that is called the single plus triplet scotogenic model, where the particle contents, you can see it in this table. The model adds 2 new fermions. One is a triplet and the other is a singlet. And also 2 new scalars, that one is a double and the other is a triplet. The first 3 are charged under the C2 symmetry and the other don't, because we want that this last particle, this triplet scalar that is labeled by omega, acquire a bed in order to mix the fermions, the fermion sector, the particles of the fermion sector in the scotogenic model. So here we have the new Lagrangian terms, the new terms in the Lagrangian. The terms that are into the orange box are the ones for the simple scotogenic model, The ones that are into the cyan box are the ones for the triplet photogenic model, and all of the terms that are into the pink box are the terms for this extension of the photogenic model. These are also the terms for the scalar potential, where we can see that are bigger in comparison with the one of the simple photogenic model. And also we have the conditions to these parameters in order that the scalar potential be bounded by below. This is the scalar sector of our model. Here we have the new doublet, where we can see that this double field don't acquire a BEV because we want to that one of them, this particle, be a dark matter candidate. We can see here the new triplets, where we can see that this field acquire a BEV. And in this work, we are focusing in, as I told before, we can consider a fermion dark matter or a scalar dark matter. In our work, we consider it a scalar dark matter for simplicity. And we choose with some choices that we did in the parameters. We are choosing the M eta real as the dark matter candidate. We are not focusing in the fermionic sector as a dark matter candidate, but you can read our work or previous work where we can where they study this sector for this photogenic model. But here we have the fermionic sector where we can see the triplet, and these are the physical masses for the model. So in this model, we have neutrino mass generation, where we can see that the neutrino masses are given at one loop, where the particles of the dark sector are the mediators. Here we have the new Yukawa couplings. And when you do a Casasibarra parametrization, you can have the new Yukawa's coupling function of some terms at the different mass of neutrinos, generic rotation matrix, the lepton mixing matrix also. In this model, only 2 neutrinos acquire mass, so this will have some implications that I will not explain here, but will have some implications in neutrinoless double beta decay. For do our analysis, we consider some constraints that are related to lepton flavor violation, to the neutrino oscillation parameters, to the electroweak precision test at 3 level, and to dark matter cosmological observation, and is the Higgs going to invisibles, and also some constraints in colliders. We use Python. We developed a private Python code, but we use some numerical tool for particle physics, as you can see in this slide. And this is our numerical scan that we consider for this work, where it's important because we consider some constraints in order to have our C2 symmetry is safe. So these are our results. This is related with the relative density, where we can see that the tiny band, black, that is horizontal, is the band measured by Planck for cold dark matter at 3 sigma. And the points that fall exactly in this band that are colored by cyan are the result that explain the total dark matter abundance that exists in the universe. The points that are in blue are the ones that are not forbidden for any constraint, but cannot explain the total dark matter abundance that exists in the universe, and are only a candidate that can be a subdominant candidate for dark matter. The points that are in dark gray are the ones that are in conflict with the current limit on with nucleon spin-dependent elastic scattering cross-section, setting band xeno 1 ton. And the points the results that are in light gray are the ones that are forbidden by any constraint that I mentioned before. So in this plot, we can explain that the first drop is the pole of the Z boson. The second one is the pole of the Higgs boson. And the third one is when quark interaction become important, and we have the annihilation of dark matter into W plus and W minus boson. Later, the dark matter mass is increasing, and it's more difficult the annihilation, so the relic density increase. Here we have the result for a spin-independent dark matter nuclear elastic scattering cross-section versus the mass of the dark matter. We can see that the results that fall into this dark green zone are the ones that were colored by dark gray in the last plot, and are in conflict with the limits imposed by xenon 1 ton. We can also see that that the points that represent the total dark matter abundance that exists in the universe falls into a vertical line in masses between the 700 and 800 GeVs. We also wanted to make a comparison with this dashed orange line corresponding to the neutrino floor limit. And also we developed some future analysis for the experiment Luke Zeppelin only in comparison. Here we have the result for under detection, where we have the dark matter annihilation cross-section into gamma rays for annihilation into BB bar that are represented by orange color, tau plus, tau minus represented by dark cyan color, W plus and W minus represented by dark red color. The points that are in like red are the ones that represent the total dark matter abundance that exists in the universe. We can see that the dark cyan, red, and orange lines that are plotted here are the current limits for setting by Fermi-Lat satellite. So the points that could fall into this dark zone are the ones that are excluded. And also the points that follow into this dash dot line are the ones setting by Hess telescope looking the galactic center into annihilation of W plus and W minus boson. We also developed some expectation for future experiments. So we have this dash black line that is for the CTA looking at the galactic halo for an isotope profile of dark matter annihilating to W plus and W minus bosons, and the dash orange line for Fermi-Lat satellite annihilating into BB bar. So we can see that there are some points that could be tested in mass in the mass range between the 60 or 70 GeVs, and for larger masses into the around 100 GeVs that could be tested for future experiments. After that, we consider analysis in colliders for dark matter. So we consider a monojet signal, where these are the main diagrams that appear in our analysis. We choose one benchmark point that is a subdominant candidate of dark matter, and we test our result with a checkmate in order to be in agreement with the result of the LHC. Here we have our result for the cross-section going into proton-proton into dark matter plus jet, proton-proton to invisible plus jet, where in both, the first one is where the mediator is the Higgs boson and the second is the Z boson. We can see that there is an enhancement of the cross-section up to masses around the 60 GeVs. And the mean one, because when the Z boson is the mediator, we have co-annihilation. When the Higgs boson is the mediator, we have annihilation. The mean one is the contribution of where the Higgs boson is the mediator. As summary and conclusion, we can see that due to the large parameter space of the singlet plus triplet photogenic model, we can obtain some main results, and that they are in agreement with all the constraints that survived, all the constraints that were imposed explicitly, the ones imposed as xenon 1 ton. We have some results that are very interesting in the under detection, that could be tested for future experiments. We also have some important enhancements to the cross section that could be tested at the LHC. Thanks.
Thanks a lot for this very nice talk. So are there any questions or comments? Maybe I use the raise hands button.
Actually, if I can, maybe I have a question.
Yes, please.
It's Michal. I didn't understand what's actually stabilizing the dark matter in this class of models that you were talking about. I mean, there seem to be scalars with different Z2 parities in the field list. Do they all get mixed within the dark matter mass eigenstate or not?
Not. The ones that stabilize the dark matter is the Z symmetry, so this doesn't acquire a BEP, and this is how we stabilize the dark matter. The only that mix are the fermions, but the scalar sector don't.
The scalars do not mix among each
No.
other. Okay, that explains it. Okay, thank you.
Thank you.
Okay, so are there any urgent questions? If there are. So it seems not. In that case, thanks the speaker here.
Okay,
so we move on to the, thanks. We move on to the next. So now we switch to the exotics session here. So Federico? Yes, thanks for sharing. So our next speaker is Federico Scutti, who will be talking about the search for heavy particles with leptons at Atlas. So please go ahead.
Hello, can you also see myself?
Yeah, yes,
okay,
yes,
cool.
both, yes, thank you.
Very well, thanks. So I'm going to talk about Atlas searches for heavy particles where the final state includes leptons. In this talk, I will often discuss a relatively simple final states generated by decay chains involving heavy neutral or charged leptons or bosons. And as you can see from the slide, there is a large number of models predicting these new particles. So while we are certainly considering the interpretation of these results in their respective frameworks, we're also interested in setting a more general and model-independent interpretation of our conclusions. The searches I will present include only results taken from proton-proton collisions at 13 TeV in run 2 and range in integrated luminosity from a fraction of the dataset where the analysis will be updated in the future up to the entire dataset of 139 inverse femtobar. As I was mentioning, these final states are often simple, where we have just two same flavor leptons and where we consider either resonant or non-resonant kinematic configurations, or a simple lepton and missing trans energy. However, for more complex topologies, I have named a few searches to be of the semi-leptonic type, where the final state also includes jets. These are mostly motivated by the seesaw mechanism of type 1 and type 3. And for type 1 only, there are two versions where all objects in the final state are resolved and reconstructed individually. And also one version where two jets in the final state are merged, which is focusing on boosted decay kinematic of heavy type 1 seesaw neutrino. Now, all the searches feature light leptons in the final state, meaning just electrons or muons. Atlas has looked for a resonant dielectron or dimuon pair in this search, considering the mass range between 250 GeV and 60 eV. The main backgrounds here are Drell-Yan and top quark pairs mostly, with a smaller contamination of multi-jets and W+ jets. The background is entirely modeled using a data-driven method by fitting data using a function where the choice of the functional form is performed using simulation, but its parameters are fitted to data. This is a non-relativistic Bragg-Wigner, which is also the model for the signal plus background, where it is considered at various width convolved with the detector resolution. The left plot here is showing the local significance of any excess over background as a function of a generic mass in the zero width approximation, meaning where the peak width is only the Gaussian experimental resolution. And the plot on the right is the observed fiducial cross-section upper limit for various width over mass ratios, which also shows overlaid the cross-section of the sequential standard model Z prime production at the RC. As you can see, the intersection is at 5 TeV, which is a pretty impressive result. A second search is set on the same final state, essentially, where the benchmark signature this time is a 2-quark, 2 leptons contact interaction. So basically a non-resonant kinematic configuration. And here the signal would show up as a deviation from the expected gradient of the high mass tail of the mass spectrum. The model is reported in this box, where in addition to the Drellian contribution, we expect a Drellian versus contact interaction interference term and a pure contact interaction term. These terms are parameterized by the scale of the contact interaction lambda, the factors Fi and Fc, which depend only on the mass, and for the interference term, the character structure of the model, eta ij, where I and j run on the left and right-handed degrees of freedom. The background is constrained in a low mass region and extrapolated to the single beam signal region. And as you can see here, signal regions are defined such as to avoid the deficit of destructive interference terms with respect to data. The background model is the same I've introduced for the resonant case, and it's fixed using a control region which is checked against signal contamination. On the left here, you see the model independent upper limit on signal events, which is considering signal categorization between constructive and destructive interferences. While on the right, you see the exclusion limit obtained scanning the parameter space of lambda and the chiral parameters. Another search is set for heavy charged bosons decaying in a lepton plus a neutrino, where the observable is the transverse mass of the event, constructed using the lepton momentum and the total transverse energy. Here the backgrounds are modeled using the simulation, with the exception of the multijet one, which is data-driven. And the exclusion limit is presented on the left, which is showing the exclude cross-section in the entire phase space. And the one on the right only considers a fiducial cross-section, where the low mass tail of the signal is cut out. The observed exclusion here is obtained, as you see, for different values of the width to mass signal ratio. Moving on to sort of more complex final states, Atlas sets a search for heavy neutral and charged leptons, leading to decay chains containing 2 leptons and jets in the final state. 2 example diagrams are shown here, featuring same charge and opposite charge configuration of the leptons, which are considered for an independent optimization of the analysis. In addition to these leptons, we also require 2 resolved jets with invariant mass consistent with the W boson. And the final discriminant for the search is the scalar sum of all transverse momenta and missing transverse energy in the event. The backgrounds are constructed using different mixtures of control regions, and their model is validated using control selections, as you can see in the left plot. On the right, you see the exclusion limit, where the only parameter of the model is the degenerate mass of the charged or neutral states, these sigma particles, which is also showing the cross-section of the type 3 seesaw model. Another semi-leptonic analysis considers 2 leptons and jets in the final state with no missing transit energy and only lepton pairs of the same flavor. The research expects to see 2 beyond the standard model particles, which are 1 heavy neutrino and a W boson within the context of a left-right symmetric model, where their masses are free parameters. So there are 2 kinematic regimes in the search, depending on the mass hierarchy between these 2 heavy particles, where we either reconstruct the W mass using both leptons and jets, or only the 2 jets. Similar to the previous search, the analysis is split into an opposite charge and same charge categorization of the final state, and backgrounds are considered again in control regions and validated in the appropriate regions. The reason to use the charge product as categorization of the selection is to discriminate between the Majorana and Dirac neutrino hypothesis, where Majorana neutrinos would lead to opposite and same charge channels to contain 50% of the channel, of the signal, while Dirac neutrino would only show up in the opposite charge channel. As you can see in these 2-dimensional limits in the mass space, the 2 channels yield a similar sensitivity as they individually feature similar sensitivity. Finally, the same model and decay channel is studied in another analysis focusing on a boosted regime, where the heavy neutrino is produced with large transverse momenta. So an entire portion of this diagram would be merged into a single large radius jet with a transverse momentum above 200 GeV, and which would contain the subleading lepton in the event, while the other isolated lepton is required to recoil with respect to the large radius jet. The invariant mass of the jet and the isolated lepton is then reconstructed, and the final exclusion limit is shown on the right here, where you see that the observed exclusion is extended beyond the boundary of the result search in blue. So just to quickly conclude, what I've shown here are results including fresh new data and slightly older ones with a reduced data set. Just to mention here that new updates are going to be performed by Atlas, not only in terms of considering the entire data set on other analysis, but also in terms of extending previous signatures. So definitely stay tuned for more interesting results, and thank you very much for your attention.
Thanks a lot for the very nice talk. So are there any questions or comments? So in that case, I have one. So you, on your conclusion slide, you said there are more results to come. So maybe could you briefly mention that?
Well, first of all, one analysis which I presented is actually still preliminary, so but it will be published very soon. Another example, there are quite a few other analyses in this general area of searches which I didn't present, unfortunately. But for example, I can think of WCR6, which already has a result out from Atlas with a reduced data set, and which is also in course of finalization of the publication. Yeah, so this is one example.
Okay, very good. Thanks a lot for the answer. So more comments or questions, if there are? it seems not. In that case, thank the speaker again. And then we move on to, thank you. We move on to the next talk. So, Priyanka?
Yes.
Yes. So maybe could you try the share screen? So
yeah, sure.
Okay. So next speaker is Priyanka Sarma, who will be talking about the G polarization as a proof of anomalous gauge Higgs coupling. So please go ahead. I can see your slides.
Yeah, thank you. So hi everyone. I'm Priyanka, and I'll talk on jet polarization as a probe of anomalous gauge Higgs couplings. So here is my plan of the talk. Okay, so as we know that after the discovery of Higgs, the focus is on the precise measurements of its coupling to all the standard model particles, and among them, the gauge Higgs coupling plays an important role as it is key to understand the mechanism of electroic symmetry breaking. And to do that, one would need not just the total cross-section, but more observables. And one observable that has got much attention in recent years is the spin polarization of massive gauge boson that can provide deeper insight into the underlying physics. So in this work, we focus on to use the information contained in the polarization of electroic gauge boson to study its coupling to Higgs using the spin density matrix formalism. So basically, we study the Z Higgs vertex, which is represented by this black bob in this diagram at the E plus E minus and at the LHC. And this Z Higgs vertex, it takes this Lorentz invariant structure where these form factors A, B, and B tilde are in general complex form factors. And the first two couplings, it corresponds to the CP even terms in the interaction, whereas the third, it is odd under CP. And also in standard model at tree level, this A is unity, AZ is unity, but B and B tilde vanishes. So in this work, we study this anomalous couplings B and B tilde with the help of the spin polarization observable of G boson that's produced in this process. So let's quickly go through the formalism that's been used. Okay, so as we know that, that the density matrix can be expressed as a sum over certain standard matrices. So for example, for spin 1, the 3x3 spin density matrix can be written in terms of the spin operators denoted by SM and 5 rank 2 tensors denoted by this TM, which are built out of this SM. So the coefficients, which are this expectation values of S and T, these are the 8 independent coefficients, which are known as the multipole parameters. So to fully describe a 3x3 density matrix, we require this 8 multipole parameters. Now we expand this to a relativistic process where we consider a process where this V is the massive gauge boson that is produced and it decays to 2 fermions in the rest frame. So now the total rate for this process can be written as it is seen in equation 1 is given in terms of the product of 2 matrices where this P, bold P, is the polarization density matrix for this gauge boson, and what it gives. So this polarization density matrix, it contains the information about the production mechanism of the production of the gauge boson, and in terms of the production density matrix rho, it is given in equation 2, and this rho is constructed from the helicity amplitudes. Now this polarization density matrix can be parameterized in terms of the 8 multipole parameters. 3 corresponding to the polarization and 5 corresponding to the alignment components. So now one can rewrite or express this polarization density matrix, which is given in equation 3. Then one can write the decay density matrix for this interaction vertex in its rest frame, and it is given in equation 4, where this theta and phi are the polar and azimuthal angle defined in the rest frame of V, and alpha is the polarization analyzer. Now one can rewrite the total rate, or one can rewrite the angular distribution of fermions in the rest frame of this V, and in terms of this 8 polarization parameters, so we have this now this form of angular distribution of fermions. So now to extract this 8 polarization observables at production level, one can have various combination of the elements of the polarized density matrix. So here we have all the polarization observables in terms of the which is obtained from the combination of various combination of the density elements, where this for example this rho t plus 0 is the 1 0 element of the polarization density matrix, and thus we get all the 8 polarization observables. Now in real experiment where this the V, or the case boson, decays to 2 fermions, one can extract this polarization observables by putting appropriate cuts in the angular distribution of its decay products. So hence we get 8 angular asymmetries, which are denoted by this A, corresponding to corresponding to the 8 polarization observables. And hence we have this equations. As you see that this formalism connects the spin polarization observable of the massive gauge boson to the angular asymmetries, which are constructed from the angular distribution of its decay products. So any new physics interaction that's playing a role in the production mechanism is expected to change the kinematic distribution of the decay products, and hence it will change the expected to change this 8 angular asymmetries. So in this work, we intend to use this 8 angular asymmetries corresponding to this 8 polarization observables to estimate bounds on the anomalous coupling. So here we present the helicity amplitudes for this process. So the first 2 entities in M denote the helicities of electron and positron, and the third is for the G boson that's produced. And to calculate this, we use this representation of polarization vector of Z given by equations 6 and 7, where theta is defined as a polar angle made by Z with respect to the incoming electron, which is coming along the positive G axis. Here we show the sensitivities or 1 sigma limits that we have estimated on the couplings for the case of 500 GeV center of mass energy and 500 femtobarn inverse of integrated luminosity, and we do it for both unpolarized and polarized E plus E minus beam that are expected to be available in the future E plus E minus collider. So here in the first column we place all the observables which are sensitive to this various anomalous coupling, which are in the second column, and third and fourth are the limits, 1 sigma limits on those couplings. The third column is for the unpolarized case, and the fourth is for the polarized case. So there are a few important things to note from here. First is that the sigma, the total cross section, is sensitive to only one coupling, which is the real part of BZ. So in this case, to at the other angular 8 angular asymmetries, that plays and gives an interesting handle on the other anomalous couplings which don't appear in the total cross section. Then secondly, in standard model, out of the 8 asymmetries, only 3 of them are non-vanishing, which are this AX, AX square, Y square, and AZZ. And the other 5 asymmetries, they vanishes at 3 level in standard model. So, and out of them, the asymmetries AY and AXY, they are the CP odd observables. And in presence of the anomalous coupling, they got contribution from the CP odd coupling. So in experiment, if any non-zero contribution to this asymmetries AY and AXY would clearly indicate the presence of CP violating new physics interaction. Then third is that, as I mentioned, we have done this for both unpolarized and polarized beam, and we find that out of all possible combinations of the polarized, longitudinally polarized beam, the case with the opposite sign polarization, which we show here, the fourth column, it places the bounds for this case are better than the unpolarized and the same sign polarized beams. We did this for the case of 250 GeV and 2 atomic inverse of luminosity, integrated luminosity, and the same observations for the asymmetries can be made here also. And now further, if you compare these two cases, we see that the limits get slightly improved as one increases the center of mass energy. And also we find that minimal acceptance cuts, it doesn't changes much, doesn't lead to much changes on the observable. We see a less than 1% change in all the observables. Then we do the same exercise for LHC, considering the same form of the vertex, and we estimate the 1 sigma limit on the various couplings from this 8 angular asymmetries, which are calculated up to linear order in couplings at 14 TeV LHC. So in case of LHC, we see that due to the symmetric nature of this collider, most of the asymmetries, they got vanished. So to have non-zero values of those asymmetries, we need to have a proxy G direction, so which we define to be the direction of reconstructed momentum of combined Z Higgs. Here we show the sensitivities of different observables to the couplings. So you can see the y-axis we have plotted sensitivity, and x-axis is the coupling. And for the plots on the top panels, we see that the total cross section, which is denoted by this green dots, is seen to be more sensitive to this real BZ and imaginary BZ. So we expect better bounds on these couplings from the total cross section itself. But for the plots in the bottom panel, we see that, for example, for real BZ tilde, we see that the observable AXY, it's seen to be more sensitive, and hence places better, the bounds from this observables are better on this coupling. And also for imaginary BZ tilde, we see two observables, which is this AXZ and AZ, which are seen to be, which are found to be equally more sensitive to this coupling. It places a better bound on this coupling than the other asymmetries that are contributing to this coupling. So and here we summarize the plots in the table. So we estimate the best 1 sigma limit that is estimated on these couplings, and which is obtained from these various observables. Okay, so I'd like to summarize here. So we study the anomalous jet Higgs vertex by making use of the full density matrix of G boson at E plus E minus and LHC. So, and it's important to have full information about the anomalous coupling. It's important to go beyond the usual helicity fractions, and it's important to consider the off-diagonal contributions of the density matrix elements. So this is something we show here the contributions of the off-diagonal parts of density matrix also, and we see that in case of 500 GeV plus E minus, we see that most of the 1 sigma limits are of the order of a few times 10 to the minus 3, and also we find that beams with opposite polarization, it provides better limits on the couplings, and we adopt the same formalism to estimate the 1 sigma limit on the couplings for 14 TeV LHC. Yeah, thank you.
Thanks a lot for this very nice talk. So there are one or two urgent questions to this talk.
Okay, can I have a question?
Yeah, sure.
I'm sure the anomalous couplings of yours have been extensively studied before, for instance, in the Higgs to ZZ decay and then for leptons, for instance. So how do your results compare to those studies?
Atlas and CMS have put bounds. I've already put bound on this couplings, as I mentioned. So they have considered first that these couplings are real. So they have put bounds on the real part of BZ and real part of BZ tilde, and we see that they are almost. I mean, we get some comparable limits, like they are of the order of 10 to the minus 2 that we see. And so in our case, we consider both the imaginary part, we consider both real and imaginary part, and for some observables we see that the limits are slightly improved for the couplings.
Okay, thank you.
All right, so are there more questions or comments? If not, in that case, thanks the speaker again. So now we move on to the next. So Martina?
Hello, can you hear me?
Yes, very well. So could you try the share screen?
Yes.
Yes, now we can see you. Okay, so next speaker is Martina Witt. So we'll be presenting a search for the heavy neutral lepton at CMS. So please go ahead.
Yes. So good morning. I'm Martina, and I'm going today to introduce the search for heavy neutral lepton at CMS. So first of all, what are those heavy neutral leptons, or HNL? Those are right-handed neutrino, and in my opinion, they are one of the best and most elegant extension of the standard model, which can also be a solution for some of the problems, like the fact of the mass of the neutrino. They can be dark matter candidate or the baryon asymmetry. Those objects are sterile. What does it mean? It means that they can interact with the neutrino only through the mixing, but that also means that they have quite low rate, because it depends on the magnitude of the mixing with the standard model neutrino. And on the bottom plot, it's like a money plot, and it's going to be shown through the slides. It's very important because it puts in relation these two variables, so the mixing on the y-axis and the mass of the neutrino. And here the constraints, the Zixi constraints in the future projection are shown, and they show also which is our goal. So to complete and to cover all this phase space, trying to exclude as much as possible or to find something. And this is the beauty of the HNL search and the HNL fields, because in this way we have a synergy between different experiments, and we can use different experiments with their feature and with their optimal scenario to probe different masses. Like for instance, if we want to probe masses below the mass of the kaon, then NHCC2 is the best experiment. Or like for instance, mass below the mass of the mesons D and B, then BEL or LCB are the optimal one. While above for larger masses, then we enter in the domain of the LAC, so the Hadron Collider nowadays, or the Lepton Collider like LEP in the past. So going now then to LAC, which is the best, or the one that now is published, the best production mechanism for the HNL. So for the moment, the one published is always with the W production. So it means that the W decays in a lepton, and in the standard model neutrino, this neutrino oscillates in the HNL. This kind of production is very useful, and it's used because then you always have a prompt hard lepton in the initial state that you can use to trigger. In the bottom on the right, if you can see it, you see which are the mechanisms, the production mechanisms used as a function of the neutrino masses. So for instance, for low masses, the Drellian current is the one with the highest cross section, while if we go to larger mass, also the vector boson fusion becomes quite important. So like a W gamma fusion. Then the HNL decays in the W, in a Z, or in a X. But it's important to remember that there is also another variable, that is the lifetime of this neutrino, that depends on the mass and on the coupling. And in particular is inversely proportional to the mass to the 5. So if we want to study this left corner in the bottom plot, in the bottom sketch, we need to integrate our searches also with the searches considering the display signature. But today I'm only going to concentrate on the prompt signature in this talk. The last brick for the setting of the talk is about the possibility to have two different final states according to the decay of the W. So if we consider the W decaying hadronically, we have two leptons and two jets. In this case, we can reconstruct very well the mass of the HNL, but then of the jets is mass in Atlas. Then we also have the decay, the leptonic decay of the W. So we have 3 leptons in the final state plus a neutrino. So it means that we cannot reconstruct the mass, but CMS Atlas are able to identify electron mu down to few GeV. So we are sensitive at low masses of the HNL. And the last part is about the sign of this lepton 1 and lepton 2. So if the signs are the same, so the decay violates the lepton number, then we can probe like the Majorana nature of the HNL. If the signs are opposite, so the decay conserves the lepton number, then we can probe the Dirac on the Majorana. So in this way, we also have this handle in the search to probe 2 different natures of the HNL. So I'm going now to the first analysis. This is the HNL in 3 lepton final state. So we have 3 lepton in the final state. We consider them to be prompt, as I said at the beginning. We have 3 lepton plus a neutrino, so we cannot reconstruct the mass. And for low masses, those leptons are quite soft, as you can see in this plot. So we lose a bit in efficiency for signal efficiency. It's also important in these slides to show the first categorization for this analysis. That is the difference between events with an opposite sign, same flavor pair, like in this case, and without an opposite sign, same flavor pair. And you see immediately the reason why the categorization was introduced, the fact that there are almost 2 orders of magnitude difference in the background. And also you see the main background in both categories, that is the one from non-prompt lepton, so TT bar or Drellian, where the 3rd lepton is misidentified, for instance. The second categorization is the one that depends on the mass of the neutrino. So it can be divided in low mass region and high mass region. Low mass means that the neutrino has a mass below the mass of the W, so the W is on shell. High mass, it means that the neutrino has a mass above the mass of the W, so the W is off shell. And it changes completely the picture in the final state. So the kinematic distribution, for instance, of the mass of the PT or of the object in the final state. To summarize all these characteristics and these features, you have a plot here of the search region bins. It's quite complicated, but you see on the left, the low mass search bins, and on the right, the high mass search bins. You can appreciate the different background composition and the different yields. Like this part does not have opposite size and flavor pair in the event. This part has opposite size and flavor, so you see the difference. And you can also see the search region variables. And the one that I want to mention, for instance, is the mass between the two leptons in the final state. that of course is not the mass of the neutrino, but is a proxy for the mass of the neutrino. And these are the final results, and were obtained with data collected in 2016 by the CMS experiment, so almost 36 inverse of femtobar. No deviation from the standard model were observed, and the upper limit were set on the single coupling with muon and with electron. Those were the first direct limit at the moment of the publication above 500 GeV, and the first direct limit at the Hadron Collider below 40 GeV. And the shape of the limits is quite interesting. I want to comment it. So at high mass, of course, we know that the W is off-shell, so we lose in cross-section because of the off-shell W production. So the sensitivity, it's worse. Then at low mass, there is this huge correction due to the lifetime correction, as we call it, because as I said, we cannot consider anymore the decay to be always prompt. So we had to reduce the acceptance of the analysis that was designed for prompt decays. And this is why the limits from this dashed line, they go up to here for the lifetime correction. Now the second analysis is very similar, but we change the W decay. So now we consider hadronic decay of the W. So we have two same-sign leptons in the final state and at least one jet. And in this case, the reasoning is very similar. So the number of jets, so the search is split in several jet content categories in order to accommodate the different mass regions of the HNL. For low mass, maybe one jet can be cannot be reconstructed, fails the reconstruction. So we have only one jet in the final state. Then there is the intermediate mass with two jets. And then the very high mass, we have the very boost HNL. So the decay products are pretty collimated, also the W, the two jets from W. So then the two jets, they merge in one fat jet. The backgrounds are similar, but there is an extra that is the one for mismeasured charge. So the background, the Drellian background that enters in the search region when one of the two electrons is mismeasured, the charge of one of the two electrons is mismeasured. And of course, is negligible for muons. The strategy, in this case, was different and was chosen to be for each mass, a search region was optimized. So there are as many search regions as the masses that we want to analyze. But all the search region, they use the kind of the similar search region variables, so mass related. And as you can see in the plot in the bottom, you have the two plots for two different signals with the mass of the 4 objects in the final state, 3 or 4 objects in the final state. It is very useful to disentangle, to separate the signal from the background. Those are the results, again obtained with 2016 data. No deviation from the standard model were observed. And those are the first direct limits above 1.2 TeV and the most stringent one above 430 GeV. Also with respect to the 3-lepton analysis, because we gain in cross-section for the W that decays hadronically. But for the low mass, actually the 3-lepton analysis performs better for the reason that I said before. So due to the fact that we suffer for the quite high PT threshold on the jets. But very interesting is the third plot, that is the mixed coupling that was done for the first time, because it cannot be probed in an unambiguous way in the 3-lepton channel, but in 2 leptons plus jet can be. And you also see, and you can appreciate the huge improvement respect to the ATV analysis. Then the last analysis is the search for heavy right-handed W, decaying an heavy right-handed neutrino. That was presented also by Federico from Atlas. And in the final state, we have 2 same flavor leptons and 2 jets. This is a left-right asymmetry model extension of the standard model. So we consider the couplet of right-handed neutrino, right-handed W to be the same as the left-handed one. And we consider again as a search region variables, the 4 object mass in the final state. And we have 2 categories according to the flavor of the lepton. So 2 muons, one category, and 2 electrons, the other category. The background are mostly dominated by TT bar and Drellian plus jet, and they were checked and predicted in 3 control regions. The results are shown here, obtained using data from 2016 in the same way. The search region variable was indeed the mass of the 4 objects in the final state, and the windows of this mass were optimized in order to minimize the expected upper limits for the right-handed W cross-section. So no significant excess were observed, but here you can see in the top and the bottom the limits for the W right and the W cross section as a function of the mass of the W or as a function of the mass of the W and the mass of the neutrino. In the top plot, the mass of the neutrino was fixed to be half of the mass of the W, while in the bottom plot was scanned. And the mass of the neutrino was excluded up to 4.4 TeV when in the top plot. So when the mass of the neutrino was fixed to be half of the mass of the W. So to conclude, CMS has participated in the HNL hunting, and a lot of searches were brought up and extended up to TeV, mass of TeV. All the analyses that I presented today were carried out with 2016 data, but the new results are coming out with a full run-tune, so 16, 17, and 18 data. And there are a lot of developments underway. And maybe this is a personal bias, but a really interesting one is the fact that if we want to really explore the left corner that I showed you before, so increase the sensitivity at low HNL masses, then we need to integrate the prompt searches with the displaced one and start to introduce these new analyses that are indeed underway, coming out soon with a displaced signature, both in 3-lepton and in dilepton plus jet final state. Thank you.
Thank you a lot for this very nice talk. So are there any questions or comments to this talk? Yeah, so Federico?
Thanks for the very nice talk. Maybe just a very naive question. So you say in this last slide about a new analysis concentrating on displaced vertices.
Yes.
If I understood correctly, in the current version, the current published results from CMS, you just apply a correction
yes.
On the signal. So for this new round, do you have some more should I say, particle level tool, like a dedicated reconstruction for displaced vertices, or are you going to use again a correction?
No, the analysis is going to be designed to be more display sensitive, like what the one that was shown, presented here was just prompt. So this is why we had to apply the correction, where in this case it's going to be vice versa. So the acceptance is going to degrade, going to higher mass because it's going to be more displaced design rather than prompt design. CMS, a difference with Atlas. Atlas already published the HNL results with displaced signature for muon coupling only last year. While for Atlas, as far as I know, you need a different reconstruction, a second step in the reconstruction to include a display signature. In CMS, we can use the standard reconstruction with some modification, but it's not a second step, a posteriori step. So it's the usual particle flow with some different collections, but it's going to be pretty standard from the analyzer point of view. I mean, doing the comparison with Atlas. That is a huge difference between Atlas and CMS on the displaced signature.
Okay, thank you very much.
Also because the analysis that is coming out is not so displaced. So the maximum displace is going to be around meters, 1 meter, 2 meters. So still inside the inner tracker, so 1 meter. In case we want to extend that search up to the muon chambers, that is another story. And then we would need, of course, a different reconstruction that we cannot be extended up to 10 meters where the muon chambers are.
Thanks.
Okay, thanks a lot for this very nice discussion. So further questions can be asked in the Mattermost or maybe in the discussion session later. So we are a bit behind the schedule. So now we move on to the next talk. So Elena, are you connecting? Yeah. Yes. Okay, so could you try the shared screen? Yeah.
Sure.
So yeah, you can try the full screen. Yes, right. So our next speaker is Elena Dallocco, who will be talking about the exotic surges at the LHCb. So please go ahead. Maybe could you try the full screen? If it's not full, then fine. But
no, it should work now. You should.
Yeah. Yes. Thank you.
No problem. Right. Yeah, I will give you an overview of the exotic searches that we perform with the LSCB detector. So earlier this morning, you already heard about the LSCB detector. So we just here I just want to point out that we have very good vertex and mass resolution, which allow us to probe area of the parameter space, especially at low masses and low lifetime. Now, in terms of exotica searches, the trigger is very important because we can take advantage at the hardware level of the very soft trigger that we have, and at the software level of the fact that we have both particle identification and jets already in the trigger, and we also have a specific trigger on the touch vertices. So this makes LSCB excellent for light muon searches, both prompt and detached. So here, to give you an idea, I put the most recent searches that we performed with this signature. But since you already heard about most of them this morning, I will just focus on the search for a light spin 0 boson 5 that decays promptly into a dimuon pair. So this can be produced in various mechanisms, but the ones that I will show you today is where it's produced directly from PP collision via gluon fusion. But the search is being designed to be as independent as possible from the different models. So the search is in kinematic beams. So as you can see here on the left, we have 2 beams in pseudo rapidity and 6 beams in transverse momentum. Now, one of the main backgrounds is represented by the Rayleigh processes, and this one is irreducible. But we have other backgrounds that actually we can keep under control. So one is given by heavy flavor decays, and or another background is where you have one muon from heavy flavor decay that is combined with a prom muon or a pion that is misidentified as a muon. And both these categories backgrounds can be suppressed by using a uniform boosted decision tree classifier that has also the advantage that minimizes the dependence of the efficiency on the mass. As you can again see in this plot where you have 3 mass points and the efficiency is pretty close for all of them. Why is this important? Because the idea is that we fit the dimuon mass with different mass hypotheses for the signal. And the peculiarity of this search is that we could actually probe regions very close to the upsilon resonances. So here is a zoom of the dimuon resonance near the resonances. And you can see that thanks to the very good control of the tails, because they change quite a lot between kinematic beams, we could actually probe also the regions in between the resonances. And this, unfortunately, no signal has been observed, so a limit has been set as a function of the mass of the boson, which is comparable with the most stringent existing limit from CMS. But as you can see here, we got very close to the resonances, as I mentioned earlier. Now, another search that exploits the high reconstruction efficiency of the muon, and this is the first time it is presented, the paper is in preparation, is a search for a prompt heavy neutrino decay of the W boson. So the W decays into a muon and a heavy neutrino, and the heavy neutrino into a muon and a jet. And we consider both lepton number conserving and lepton number violating decays, so where the 2 muons have opposite sign or same sign. The mass range covered is between 5 and 50 GeV. So it's similar to the searches that Martina just mentioned in her talk, but differently from Atlas and CMS. So you saw that CMS tends to, at low masses, is more sensitive by using fully leptonic decays of the heavy neutrino because they have high threshold on the jets. In our case, we have much lower thresholds, so that's why we went for the semi-leptonic decays of the heavy neutrino, especially because if you look at this plot on the left, we have a branch ratio which is higher than 50% if you combine the different final state. Now, another thing to consider that will be important for the result I show you later, as already Martina has mentioned, the heavy neutrino at low masses can be long-lived. So especially for a 5 GeV mass, you see that you can have a lifetime up to tens of picoseconds. Now, the strategy of the analysis consists in dividing the data set and orthogonal control regions, which are enhanced in the different backgrounds, where the main backgrounds are electroweak charge and neutral decays, heavy flavors, so V bar and CC bar, and light QCD. And then the idea is to set a limit on the branch ratio times decoupling by normalizing with respect to the standard model process W2 mu nu. So here in the plot, you see the fit to the normalization channel, which is split by charge in order to take into account the different production rate at LACB. Then in order to extract the signal yield, the mu-jet mass distribution is fitted according to different mass hypotheses in the range between 5 and 50 GeV. Here you see an example. And on the left, you see the case for the same muons. You've seen that we've been pretty good in reducing the backgrounds because we are left with only 8 events. But unfortunately, these are compatible with the background-only hypothesis. While on the right, you see the case for opposite sign muons, and you can notice that we have much more background due to the reducible contribution from Rayleigh processes. And this leads to having a limit which is about a factor 10 worse for the lepton number conserving decays with respect to the lepton number violating in red. Now you see that at low masses, we had to correct for the lifetime of the neutrino. So in the same way as CMS had to do, we had to do the same. So our search was designed for prompt heavy neutrino, so we had to correct for the fact that part of the neutrino instead is expected to be long-lived. And this will bring us to have a slightly worse limit that brings us from the light color to the dark color in both limits. Right. So now, bunch of searches, of exotica searches in LACB is represented by long-lived particle searches that can be divided into groups. So in the first category, we have long-lived particles which are produced in B or D decays. And in this case, the background is reduced by constraining the mass of the decay particle to the mass of the B and applying further constraint on the vertices. Or we can have long-lived particles which are produced directly in PP collision. And these are the two searches that I will show you today with displaced jets. And in this case, the background depends on the transverse displacement of the secondary vertex. Because in our vertex locator, we have an corrugated aluminum foil that separates the vacuum of the machine with respect to the vacuum of the sensor. So if your vertex is prior the RF foil, then your background is dominated by heavy flavor. If it's beyond that, then it's mainly dominated by material interactions. Now, this can be kept under control if you have a detailed material map of the velo in order to veto these decays. And this is what we did. So using beam gas collisions for both Bores collected in run 1 and run 2, we could, since the gas goes through the full length of the velo, then we could use the secondary interaction of the hadrons to map the material. So you see on the left, for example, the reconstruction of the RF foil that I just mentioned, and on the right, one of the velo modules. So this has been used in many of the long-lived particles analysis. Now, the first analysis that I show you is a search for ions, so the lightest in the sector particle, which is produced via Higgs boson. And since in most cases only one of these two VIP ions is within the LACB acceptance, then what we reconstruct is a single displaced vertex with two associated jets. So the idea is that we trigger on the displaced vertex, then we apply the material veto and some requirements on the jet pointing to reduce the two main background that I just mentioned. Then we are left with a standard model, a background from standard model dijet events, which we know though that is strongly dependent on the transverse displacement. So we bind in this variable, and this here on this on the left you can see an example of the fit, and you can already notice that the background is in very good agreement with the data. So in fact, no excess has been observed of the standard model background, and upper limits have been set as a function of lifetime and for different mass point. Now, if you map one of these branch relations to the 2D plane, then you can see the area covered in the phase space by LACB compared to other experiments. Now, the area covered by ATLAS and CMS here are from quite old paper by now, so now they're being superseded, but this plot gives you an idea of the fact that LACB tends to go towards lower masses and lower lifetime with respect to the other experiments, so it's a complementary coverage. And you can appreciate this even better if we see how this will behave when we, with the integrated luminosity that we expect for upgrade 1 and then upgrade 2, so 50 and 300 inverse femtobar respectively. you see that we extend the area covered in the parameter space. And we also, of course, given the higher statistic, probe more stringent limit. Yeah, the other search that I wanted to show you is for a massive long-lived particle that decays semi-leptonic into standard model particles, which can be interpreted according to either simplified topologies, which are represented here on the right, which are less model dependent, or in terms of R parity violating neutralinos. So the signature is the one of a high multiplicity displaced vertex with associated an high transverse momentum mu. The background is again dominated by BB bar, as you can see here in the plot on the left. But the high PT muon is exploited because it's very isolated to define two different regions in the phase space, one enhanced signal and one enhanced in the background, which are fitted simultaneously to exert the signal yield. Again, no significant excess has been observed, so upper limits have been set over the different models that I mentioned earlier. And you can also, again, extrapolate to the integrated luminosity that we will have with the upgrades. And you can see that we cover a very wide range in the parameter space. And we could also extend actually to higher masses. We don't have stimulation for it to look at, but this is definitely within our reach. To conclude, there is an increasing interest in direct searches from LHCb, especially because we can probe area of the parameter space which are complementary to the other experiments. The analyses I show you today are on run 1 data, but many new analyses are ongoing with run 2 data. And you have to keep in mind that we are also undergoing a major upgrade of the experiments. So when we will restart, either at the end of next year or the beginning of the year after, we will have 5 times higher instantaneous luminosity. And an important aspect is that we will not have the hardware trigger. And also there are several studies going on to improve the efficiency for longer decay length, as well as to access the jet stop structure that can even improve the reach of LHCb. Thanks.
Thanks a lot for this very comprehensive and nice talk. So are there any questions or comments? Maybe a few quick ones, if there are. So don't be shy, so you can ask. Okay, so since we are a bit, okay, so we still have 1 or 2 minutes indeed. But okay, in that case, maybe could you try to mention a bit more about the prospects, because you are upgrading the experiment for the round 3?
Yeah, so we are undergoing a major upgrade. So all the tracking detectors will be replaced. So this, yeah, will definitely improve our reach. But the main difference is that we will have a triggerless without. I mean, by triggerless, I mean we will not have the hardware trigger. So it means that already our thresholds that are low, there will not be. We only have requirements at the high level trigger. So this will definitely improve searches that, for example, like the Daimyon search that I showed you before, this will definitely have receive a boost from that. I don't think there are other extrapolations other than the one I show you here, but I think that, yeah, also the studies that are ongoing on, for example, jet structures or using downstream tracks. So for the moment, we just use, long tracks that cross the full length of the detector. So we are kind of limited in testing. For example, in this case, you see we are limited to the long lifetime because we are limited by the acceptance of our vertex locator. With these ongoing studies on downstream tracks, we aim at extending the range of lifetime we can cover. So I think...
Yeah, thanks a lot. Sounds very promising indeed. So if there are no more questions or comments, and in that case, so we move on. Thanks, Elena.
Hi,
Okay,
can you hear me?
Yeah. Yes, Javier. So could you try the shared screen?
Yeah.
Okay, so our next speaker is Javier Alonso Gonzalez, who will be talking about the exotic vector-like Cork phenomenology in the minimal linear sigma model. So please go ahead. So
Maybe
could you try the full screen?
Yes, I'm. Can you also see me?
Yes.
Perfect. Perfect. So let me share again my screen. Okay. Okay. Okay.
Yeah, sounds looks good. Yeah.
Okay, perfect. Hi everyone. Let me first thank the organizer for giving me this opportunity to present this talk. Focus on this topic, exotic vector-like quark phenomenology in the minimal linear sigma model, and which is based on this paper published last February. Oh, there's a problem here. Sorry. Okay. Let me now motivate the model. You all know that the Higgs was discovered in 2012 with a mass of 125 GeV. However, it seems to be light since quantum corrections to the scalar masses are strongly sensitive to the scale of new physics. This scale seems to be at least above the TV regime. So this means we could be dealing with a fine-tuned cancellation in order to have such light Higgs, unless the Higgs mass is protected somehow, like in many theoretical proposals, for instance, SUSY. Here we consider other frameworks, composite models, where the Higgs arises as a pseudo-Nangu Boston boson. The minimal realization compatible with custodial symmetry would be based on this cosahedron here, where the 4 Goldstone bosons would be the standard model Higgs doublet components. The problem of composite Higgs models is that they are effective descriptions, only valid up to some energy scale. Among those proposals that are trying to improve this issue, you can find the minimal linear sigma model is a renormalizable model that in certain limit falls into an effective description of the minimal composite Higgs scenarios. Here are sketched the main ingredients. You can see the group structure of the minimal composite Higgs models. F is the Breaking scale. The U1X is just another global symmetry added to reproduce the correct hybrid charges of the standard model. Regarding the spectrum, the standard model gauge bosons are kept, together with the 3rd generation standard model quarks. The scalar sector consists of a real SO5 quintuplet built up with the standard model Higgs doublet, together with this new heavy electroweak singlet. It's when this particle is too much heavy when the model falls into the typical effective description of a minimal composite Higgs model. The fermionic sector is also extended with 4 vector-like quarks, 2 SO5 quintuplets, and 2 SO5 singlets. The primate ones would be related to the bottom sector, whereas the unprimate ones to the top sector. And at last but not least, the standard model quarks get their masses thanks to fermion partial compositeness through a fermionic seesaw mechanism. Let's focus a bit more on the fermionic sector. Here are shown the main transformations for these new vector-like quarks. In the end, aside from the standard model quarks, the fermionic sector consists of 2 vector-like quarks with exotic charges, -4/3 and 5/3, 5 top partners with charges 2/3, and 5 bottom partners with charges -1/3. Regarding the fermionic Lagrangian, its terms and parameters are summarized here. For each sector, top and bottom, there are kinetic terms for the standard model and exotic fermions, Dirac mass terms for the singlet and quintuplet fermions, 2 Yukawa terms connecting the scalar quintuplet and the heavy fermions, and 3 partial terms between the standard model quarks and the vector-like quark ones, characterized by these scales lambdas from here. As I said before, the standard model quarks get their masses through a fermionic seesaw. In the interaction basis, these quarks are not directly coupled to the scalars. The leading contribution for the mass of the quark would be given by this diagram from here, where the parameters that enter in this contribution are highlighted here. And for the bottom, we'll have a similar diagram. Well, we are adding scalars and fermions to and this would modify the interactions of the light, the degree of freedom with respect to the standard model. And consequently, the minimal near sigma model would be constrained by those observables that depend on these modifications. For instance, there are bounds coming from those observables that depend on this ZBB coupling, since it's modified thanks to the mixing between the standard model bottom and the bottom parameters. There are also bounds from S and T oblique parameters, since we are adding scalars, a scalar and fermions that are coupled to electroweak bosons. Moreover, measurements from Higgs signal strengths constrain the mixing between the Higgs and the scalar singlet. Using a chi-square fit to the latest Atlas data, we found this bound for the mixing at a 95% confidence level. And there are also bounds from searches for heavy resonances at the LEC. Considering the latest Atlas search for scalar resonances in the boson final states, we found this blue line, which is the 95% confidence level limits on this parameter space, the sigma mass and the sine square of the mixing. To obtain this limit, this blue line, we assume that vector-like quarks do not contribute to the gluon fusion production of sigma, and only standard model tops run in that loop that contributes to this production mechanism. And it contributes with a Yukawa, standard model Yukawa, weighted by this sine square of the mixing. We've checked that in most regions of the parameter space we consider, this approximation is quite good. In addition, let me say this yellow region from here. In this yellow region, there's no SO5 spontaneous breaking. So in this model would be forbidden, this region. And consequently, only this wide region from here would be allowed by both experimental and theoretical constraints. In the end, we are just interested in the phenomenology of the lightest vector-like quarks, since they are the easiest to produce at colliders. In the mass basis, these are the interactions determining the production and decay for the lightest top and bottom partners. The different part, with respect to what standard experimental analysis consider, it's here, the interactions with sigma. These interactions lead to new possible decay modes, and together with the fact that in the sigma model, in the minimal linear sigma model, the sigma mainly decays to the standard model bosons, the possibility of new multibosonic signatures at the LHC is open. To see such signals, we need a sizable exotic branching region, and before that, we need also to produce these vector-like quarks through one of these two possible mechanisms: QCD per production and single production through the interchange of electroweak gauge boson. As an example, here are some results from a numerical scan over a region of the parameter space where the top partner is the lightest vector-like quark, and where this new phenomena could take place. On one hand, you can see that the resulting coupling between the standard model bottom, the top partner, and the W could be such that single production, here represented for two different obtained values for the coupling by the red line and the green line. Well, the single production could dominate over pair production, this blue line, even from considerable low masses. On the other hand, for a significant number of scenarios and for different masses, the exotic branching rate to standard model top and sigma is relevant, and in some few cases could be even the dominant channel. There are other regions of the parameter space where the bottom partner is the lightest vector-like quark, and the exotic branching ratio is even larger. However, single production only starts to dominate for very large masses, and with a cross-section of around the R-bar. So you won't see it at the present LHC, the single production of the bottom partner in this model. Okay, now finally, you could ask yourselves if present LHC searches are sensitive to these new phenomena, these multibosonic signals. Let's see an example in this paper from here. The Atlas collaboration targets this process from here. The QCD bottom partner production with the subsequent decay to Ws, and in the end leading to BTAC jets and either 2 same-sign leptons or 3 leptons. Apart from these final states, event requirements call for large missing transfer energy and large transfer energy. Now, this search could be sensitive to this exotic decay chain that in the end could lead to the same final result, state, sorry. Here are shown the normalized kinematical distribution functions obtained at the parton level of the missing transfer energy, the transfer energy, and the leading lepton transfer momentum. For the standard decay chain that is targeted by Atlas, represented by the blue lines, and for the exotic chain for 2 different masses of the scalar, 700 GeV, the red lines, and 1 TeV, the green lines. As you can see, these distributions that do not depend in the, sorry, by the way, the mass of the bottom partner here in these examples were set to 1.2 TeV, okay? As I was saying, these distributions are very similar and they do not depend in the individual branching ratios of sigma and the bottom partner for the bottom partner. So we could say this Atlas search is apparently sufficiently flexible to provide some limits on these non-standard better-like quark decay modes. To reinterpret the results, we would need to relax the condition that the sum of the standard branching ratios are equal to 1 in order to add the new possible decay chain. So, summing up, the minimal linear sigma model is a renormalizable scenario where the hierarchy problem could be solved. Within this model, partners phenomenology could be completely different from what experimental analysis consider. On one hand, QCD top partner production could be negligible with respect to single production. And on the other hand, both top and bottom partners could be profusely decay into the new exotic scalar singlet. That could lead to really interesting characteristic multiple sonic signals at the LHC. And finally, the new decay modes can in principle be captured by these current LHC searches if they are sufficiently inclusive. That would be all for now. If you have any questions, please don't hesitate to ask me, and thank you.
Thanks a lot for this very nice talk. So are there any questions or comments to this talk?
Okay, can I perhaps have a question, Michal?
Yeah, sure.
I mean, it was, I'm sorry, it was pretty fast for me, but I think you said that your model withstands the electroweak precision tests, right?
Yes, there are new contributions from both the scalars and the fermions. And in the backup, I have, if you want, the expressions. That, for instance, what? Sorry. Yeah, these are, for instance, in the scalar sector, the modifications from the standard model observation, from the standard model, sorry, prediction. Okay, from the scalar sector. And yeah, for the fermionic sector, the expressions are a little bit involved and they are not shown here, but they, of course, since they are Retor-like quarks that are coupled to these, that have SU2 left quantum numbers, they also would modify these constraints, yeah, these parameters. But yeah, we analyzed, during the scan, as I said before, we did a numerical scan and we ensure these constraints are respected.
Okay, thank you.
You're welcome.
Okay, so are there more questions? Maybe one or two, if there are. Okay, So in that case, thanks a lot. So
You're
now
welcome.
we move on to the last talk of our session.
Yeah.
So Denis?
Yes.
Yes, could you try the shared screen?
Yes, just a second.
Okay, so our next speaker is Denis Loy. We will be talking about the searches for heavy resonances decaying into G, W, and Higgs decays at the CMS. So please go ahead.
Okay, thank you for the introduction. So the motivation for doing searches such as these is that high mass resonances can be interpreted as new particles predicted by various beyond the descent model theories. For example, one can consider a Twixtor model, or more specifically a minimalistic supersymmetric standard model, where an additional Higgs doublet is introduced, and so there are 4 additional Higgs bosons. One can also consider a heavy vector triplet, where you have more particles, such as the W prime and the Z prime. And one can also consider a bulk graviton coming from a random Sundrum model of warped extra dimensions. And with the descent model being incomplete, searches such as these in unexplored phase spaces are encouraged. Now, before I go into detail into some of the analyses which have been released over the last year, I want to talk about something which all analyses do. So this is something which was already briefly mentioned in one of the previous talks in the session. So basically, if you consider bosons coming from the decay of a high mass resonance, then these are going to have a large Lorentz boost. And if the bosons further decay hadronically, then the jets will be collimated such that they can then be reconstructed as a single AK8 jet. This refers to a jet that's reconstructed with the anti-Kittier algorithm and a cone size of 0.8. These jets are then always groomed using the soft drop algorithm. This is a modified mass drop tagger, and this is done to remove constituents from soft wide angle radiation. So the plot you can see here on the top right shows the distribution of the reconstructed masses of W, Z, and Higgs bosons coming from a high mass resonance. And you can see that using this groomed mass, these can all be reconstructed to have a mass similar to what you would expect from these gauge bosons. Another variable which is used by many analysis is the anisotropiness, referred to as tau2-1. This can be used as a discriminating variable which determines how likely it is that a fat jet is composed out of exactly 2 subjets, and this value is closer to 0 for events where this is in fact the case. The plot you can see here on the lower right shows the distribution in an analysis with the signal being displayed by these lines here, which has a peak closer to 0 compared to the distribution of the background. Now I'd like to move on to some of the analyses, starting with this one, which considers the decay of a high mass resonance into 2 W bosons. This analysis considers a dileptonic final state and a semileptonic final state, although in this presentation I'll be talking about the semileptonic final state. This analysis is categorized according to multiple features. So first of all, based on whether the hadronically decaying W boson is reconstructed in a boosted manner, as I've just elaborated, or in a resolved manner, where there is no fat jet to be found in the event. This is likely the case in events where the signal mass corresponds to 600 GeV or less. This is also categorized according to what the events are tagged as, so either as vector boson fusion, gluon fusion, or perhaps untagged, and also by the final state lepton flavor, either electrons or muons. Event selections in this analysis include the requirements that the hadronically decaying W boson should be between 65 and 105 GeV. And for the boosted category specifically, the analysis makes use of the anisotropiness and requires that this has a value of less than 0.4. Major backgrounds in this analysis include contribution from top backgrounds and W plus jets. The analysis considers the higher mass resonance coming from an electric singlet with a descent model-like width, and this means that interference needs to be included here. So this plot you can see here on the lower right shows the distribution in black for a 700 GeV mass signal over the mass. And what you see here in red is the additional interference of the signal with the descent model Higgs boson. And in blue, you can see the interference of the signal with the non-resident WW background. And the combination of these two interference effects is shown here in green. And you can see that this is clearly non-negligible on top of the signal itself. No excess is observed over the expectation here. The plot you can see here on the top left shows the signal region of one of the categories, with in the red and blue lines being the distribution for a 800 GeV and a 1500 GeV signal respectively. So the analysis then provides results in the form of upper limits at 95% confidence level on the cross-section times branching ratio. And this is done for various scenarios with respect to the considered fraction of vector boson fusion events. What you can see here on the top right shows the limit in the scenario where only vector boson fusion is considered. And you can see here that the analysis excludes an high mass resonance of up to 1800 GeV. The analysis also provides interpretation on various MSSM and Dirichlet model scenarios, such as the exclusion limit shown here on the bottom right, which is the exclusion limit in the alignment scenario of the MH125 benchmark. And generally, the Higgs to WW channel is very sensitive in these benchmark scenarios at low values of MA and tangent beta. Next, I'd like to move on to an analysis which considers a Z prime decaying into a Higgs boson and a Z boson. This analysis considers the Z boson to decay leptonically and the Higgs boson into a pair of jets. And so the analysis is categorized also according to the production mode, either gluon-gluon fusion or vector boson fusion. Then according to what the Z decays into, either a pair of electrons or muons, or it also considers the decay into a pair of neutrinos. And then there's also a category for whether the subjets of the hadronically decaying Higgs boson are both tagged as being bottom quark jets, or if either only one or none of them are B jets. The selection in this analysis includes that for the events where the Z boson decays into visible leptons, the dilepton mass is required to be between 70 and 110 GeV. And if it decays into two neutrinos, then it is instead required that the missing transverse energy is larger than 250 GeV. The requirements on the Higgs boson is that the jet mass should be between 105 and 135 GeV. And the background analysis includes the contribution from vector boson plus jet events, as well as those involving top quarks and double boson events. In this analysis, the vector boson plus jets background is estimated by making use of a sideband in region over the dijet mass. So the plot you can see here shows this distribution. And specifically, the sidebands are defined as the region between 30 and 65 GeV of the Higgs jet mass, and also between 135 and 250 GeV. What's done in these regions is that the contribution from tops and dibosons is subtracted from their respective estimations from Monte Carlo, and then the resulting background for the B plus jets is then normalized using an extrapolation factor from the sideband region to the signal region as obtained from Monte Carlo. Also, in this analysis, no excess is observed over the expectation. The plot you can see in the top left is again a signal region plot from one of the categories, with the line here corresponding to a signal mass of 2000 GeV for the Z prime. And the analysis provides upper limits on the cross-section times branching ratio and compares these with the expectations from various Higgs HVT models, model A and B in this plot here specifically, and both of these are excluded at 2.5 and 3.7 TeV respectively. Finally, I'd like to talk about analysis which considers the decay of a high mass resonance into any pair of vector bosons. Here, a semi-electronic and a fully electronic final state is considered, but here I'll be talking about the fully hadronic final state. So this analysis is categorized according to a variable tau-1 DDT. This is a variable based on the interpretedness, but which is modified based on the designed decorrelated tagger method. This is done because it's been found that the interpretedness itself depends slightly on the parameters of the jet. So the plot you can see here on the lower left shows the distribution of the interpretedness for QCD background samples over this variable rho prime, which is defined here as a function of the jet mass and the transverse momentum of the jets. You can see there's a slope here, which clearly indicates that there is a correlation between these two variables. And what's done is that the gradient of the slope is extracted, and then it is removed from the answeriness to define this new variable tau 1 ddt. In the plot here on the lower right, you can see the ROC curve of this variable in blue, and in comparison, the regular unmodified answeriness here in orange above. And you can see that for any value of the tagging efficiency, the mistagging rate using tau 1 ddt is significantly lower with respect to the nominal answeriness. And so this analysis makes use of this variable and defines a high purity region and a low purity region. Then for the further selection, requirements include that the PT of the jet should be larger than 200 GeV, and also that the dijet mass is larger than 1,126 GeV. And the major background in this analysis is from QCD multi-jet events. The analysis does make a simultaneous fit over 3 discriminating variables at once, one of them being the invariant dijet mass, for which you can see the distribution here on the top left, and then also over the individual dijet masses of the leading and the subleading jet. No excess is observed over the expectation, and again, upper limits are provided on the cross-section times bunching ratio. The limit you can see here on the top right is assuming that the higher mass resonance is a bulk graviton, and the limit on the bottom right shows this for the HVD model B, which is able to exclude up to 3,800 GeV. And with that, I'd like to come to my conclusion. So unfortunately, there's been no high mass resonance observed in these analyses, but there have been also many more decay channels studied than the ones I've been able to show here. And these have been able to significantly improve the upper limits with respect to the limits provided by 1-1 analyses. So as a finishing remark, the plots you can see here on the left is a combination plots of various 1-1 analyses, which study a high mass resonance decaying into a pair of bosons. And on the right, you can see the same limit using analyses from 1-2. And this limit for the HPT model B has been improved from 2.4 TeV to 4.5 TeV. Thank you for your attention.
Thanks a lot for this very nice talk. So are there any questions or comments? Indeed, I have one. So, okay, you mentioned that the, okay, on the conclusion slide, that the, significant improvements were observed comparing to the round 1. So, in addition to the statistics increase, are there more improvements? I mean, for instance, in the analysis techniques and so on?
Yes, I'm not sure about the details now, but I think mainly with respect to how the background is modeled. So for example, there was this one analysis here, which defines the B plus jets background using a data-driven technique. I'm not sure if these were employed in 1-1, but well, there are always a number of improvements in all analyses.
Okay, very good. Thanks. So are there other questions or comments? Maybe one or two, if there are.
Sorry, I raised my hand.
Sorry, I didn't notice. Okay, Tanya.
Yeah, okay. So I have a question for slide 5. Or several, in fact. Okay, so the first question is for this plot on the on the bottom right. I mean, so the black line is if you forget about interference and then you plot all the interferences, but what is the total line if you include everything? So signal and background and 125 GeV, what does the distribution look like in this case? Because now you only plotted the interference, right? But there's not the contribution from the 125. There's not the contribution, sorry, from the continuum. So how does it look in total to you?
Well, from the St. Higgs boson and from the WW boson, you have a distribution of water here at lower masses, let's say maybe up to 400 GeV.
And okay. For the signal, and MX is the MWW, so it's the invariant mass of the WW system, right?
Yes.
Ah, yeah. Okay. So it's because in the legend you say mx is 700 GeV, and then there's a variation of mx. So this is the measured mass of the WW system, so to say.
Yes.
Yeah. Okay. Okay. And the second question, I mean, you have a relatively broad signal now, or a relatively broad assumption. It's 14% or so for the 700 GeV. So were there studies what happens? I mean, this can be realized in some models, but many models have much narrower heavy scalar resonances. So can you comment on how the results vary if you vary the width but keep the mass?
Yeah, so if you consider, well, I mean, I can say that I'm working on this analysis using full 1-2 data. This analysis that I show here is using only 2016 data.
Yeah.
And I can tell you that we've now considered different scenarios with respect to the relative width of the resonance.
Yeah, fantastic.
And we have seen that for different relative widths between 1% and let's say up to 30%,
yeah,
that the distribution over the discriminating variable does not change significantly.
Yeah, I mean, this I think would be very important. I mean, this was discussed in this Higgs cross-section meeting last fall, in fact, also. And so my personal comment is 30% is quite high. You will find it hard to
Yes, so the main scenario which
a model which has this broad resonance is still after taking, all constraints into account. But of course, one should look at this as well. Okay, sorry, go ahead.
Yeah, so the main scenario which we intend to use for the full 1-2 analysis is the 2% relative width scenario.
Okay, yeah, okay. But it's just, I think it's interesting for the theory community, to know how reliable the results are changing the assumptions, so to say. So,
yes.
Yeah, okay, thank you. Cheers.
Okay, thanks a lot. Yes, indeed, that was the last talk for today. So thanks a lot to all the speakers and the participants. So indeed, we can open this Zoom room until the 1 p.m. So maybe if there are any questions to this session in general, then please just go ahead. So it seems not, or maybe people can just ask. Yes, sir?
Okay, this is Michal. Can I perhaps have a question to Martina? If
yes,
she's around.
I'm connected.
Okay, great. I mean, you were talking about those heavy neutral leptons, which were produced like weekly. It was like an associated weak production through mixing with the lepton neutrino, right?
Yeah.
So that very much resembles, I mean, what's called the type 1 seesaw scenario with very low right-handed neutrino masses. I was just wondering if there are any studies ongoing about a situation when actually this right-handed neutrino, which is the dominant component of the heavy neutral lepton, is actually a member of a higher multiplet of the SU2, for instance, like in type 3 seesaw, when it's a member of even like partially charged multiplet. And I'm asking because in such a case, I mean, you can have not weak production, but also electromagnetic pair production, and look for some kind of a cascade of this charged one going to the neutral one, and then I mean, it's like what you did. So I'm just wondering whether somebody's doing something like that.
I'm not aware of it. I can check and reply on matter on. Yes. But like right now, I cannot reply. I mean,
okay, no problem. Thank you.
Yeah. As far as I know, no, but I cannot be 100% so sure.
Okay.
Okay, all right. So are there any other questions? So it seems not. So in that case, we can close today's session. So thanks everyone for connecting. And then we will have a poster session at, in 30 minutes. So please just join. And then we have the tomorrow's session at 8 a.m. Okay, thanks everyone. So now we can disconnect. So bye.
Thank you very much. Bye-bye.
Thank you. Bye.
Bye.